Welcome to my complete C++ programming beginner to expert course. In this course, you will have the opportunity to master the C++ programming language from the ground up. We will start off in this section by getting set up with Visual Studio, learning how to create a C++ file, and taking a look at the benefits and history of the C++ language. Each section goes in order, building on the knowledge taught in previous sections, starting out with the beginner level material and working its way up to intermediate and then advanced. The second half of this course, in particular, focuses on algorithms and hands-on coding using C++. The idea isn't to have you watch a video on an algorithm. The idea is to teach you the algorithm and have you apply it hands-on, so that by the end of this course, you have a pragmatic understanding of the topic, not just a theoretical one. I created this course with one goal in mind: to take a beginner programmer who's never coded in C++ and have them fluently programming in the C++ programming language by the end of the course. Whether you are completely new to C++ or to programming, or if you have some experience and are looking to bolster that knowledge, whatever your goal is, this course will help you achieve it. In programming, you will sometimes run into issues with the code. Don't worry. Not only do these videos walk you step by step through coding, but you can message me or post to the course Q&A forum, and I will answer any questions you have and help you debug the issue so that you can continue progressing through the course. After this introductory section, we will learn about the basics of C++, including what the main function does, the various built-in types that C++ supports, and both arithmetic and comparison operators. Then we will learn about user input, conditional statements, and loops. When programming, obtaining user input is a crucial aspect of many systems. Conditional statements like if, and else statements, along with switch statements, empower the programmer to control the flow of execution of the code. Loops like for loops, while loops, and do-while loops enhance your ability to write reusable, elegant code, as you can repeat the execution of code over and over without having to manually type out each iterative call. After that, we will learn about user-defined types, that is, types that the programmer can define using C++ code. These include structures, classes, and enumerations. After that comes a section on intermediate C++, which will cover concepts like the standard library, reading and writing the files, working with date and time data in C++, writing recursive code which calls itself, regular expressions, linked lists, and trees. Then we will learn about containers, data types in C++ that allow us to store sequences of values. After that, we will learn about object-oriented programming, abbreviated as OOP in C++, as we build our knowledge around the four pillars of object-oriented programming: encapsulation, abstraction, inheritance, and polymorphism. In the second part of this course, we will take a look at some of the most popular and useful algorithms in all of computer science, and how to implement them using C++ code. Next, we will learn about string algorithms. Manipulating strings is not only a topic of paramount importance in everyday coding, but also a favorite category that interviewers ask about in coding interviews. This section will give you a look at some of the most common string problems and how to approach and solve them. Then we will learn about array algorithms. After that, we will learn about tree algorithms and then linked list algorithms. Finally, we will summarize and recap what we learned in this course. Are you ready to master the C++ programming language? Then let's get started. In this video, we will get up and running with Visual Studio Code on a Mac. The first step is to open up a web browser and type in download Visual Studio Code. We can click on the result from code.visualstudio.com. From there, we will be able to download VS Code for Mac. We can click on the downloaded file to open it. It is a zip file, so we will need to double click on it to decompress it. From there, we can double-click on the Visual Studio Code application that appears. Next, we will install the extension to run C++ code, which we can do by opening up the extensions pane, which is the fifth icon down on the left side, and searching for C++ in the search bar. We can install the first one, the most popular VS Code C++ extension. If we get prompted to install the recommended extensions for C++, we can click the Install button. After a moment, we will be up and running with everything we need to run C++ code on our Mac. In this video, we will install and set up the programs and software that we need to program in C++ on a Windows machine. There is an additional step on Windows. In addition to installing Visual Studio Code and the C++ extension for it, we will also need to install a C++ compiler. By default, Macs have a C++ compiler built in, but Windows machines do not, so we need to install one. First, we can Google download Visual Studio Code. Let's click on the result from code.visualstudio.com. From there, we will be able to click the button to download the program for Windows. Once it begins downloading, let's click on it so that it opens up as soon as it downloads. We can progress through the prompts that appear until the program is successfully downloaded and installed on our machine. Once we open up the program, we can click the fifth icon down on the left sidebar, which is the extensions pane. From here, we will search C++ and download the first result that comes up, which is the most popular C++ extension for VS Code. Next, we will go to the following URL, code.visualstudio.com/docs/languages/CPP, which has the steps for installing a C++ compiler for Windows. The one we will use is MSYS2. We can click the installer link and download the latest version of the installer. After following the prompt, a command line interface should open up. In step 6, there is a command we will need. We can copy it. And we can right-click and paste the command in there, being sure that no other characters were entered in when we pasted it. Then we can hit enter to run the command. Once that command finishes executing, we can go inside of our C drive. You should see a MySys64 folder inside of there, and we can double-click on it. Inside of there is a Ming W64 folder, and inside of there is a bin folder. Inside of that folder should be a bunch of executable files, which means that we successfully installed this C++ compiler on our Windows machine. In this video, we will learn how to create a C++ file in Visual Studio Code. A C++ file has the .cpp file extension. When we open up Visual Studio Code, we can go to File, New File. Then when we save the file, we will have the option of selecting the file type. We can either manually give our file a .cpp file extension, or we can use the drop-down to set the file type to C++. The end result is the same. We now have a saved C++ file on our machine that we can use to write the code samples for this course. In this video, we will create our first C++ program, a Hello World program. If you are new to programming, it is a tradition when learning a new programming language to start out by outputting Hello World to the console. At the top of the code, we will type #include, and then the word IOStream inside of angular brackets. This imports functionality that we can use pertaining to input and output. In particular, we are interested in outputting the value Hello World to the console for this program. #include tells the program to include a header file, which contains some code that we can use in our program. The name of the header file always goes inside of angular brackets, as seen here. Next, we need to tap into C++'s main function, which we can do by typing int main, and then a set of parentheses immediately after the word main. To define the body of the main function, we add an opening and closing curly brace. Int is the return type of the function. If the program doesn't have any errors, this function will return 0. The main function is the entry point of our program, defining where the code should begin when we run the program. Now we still need to actually output the phrase hello world to the console. To do this, we will use a cout statement, a standard output stream. We will type std, which is how we reference the standard library, and then 2 colons. After that comes cout, and then 2 less than signs or opening angular brackets. This is the put2 operator, which will be discussed in more detail in the next section of the course. We will type hello world inside of double quotes, which represents the string data type. To end a line of C++ code, we use a semicolon. If we run the code, notice that the console opens up and displays hello world, the message that we printed to it. Nice job. In this video, we will look at an overview of the C++ programming language. By the end of this lecture, you will be able to identify the key features of the C++ programming language and its role in the larger spectrum of programming languages. Some of you may have prior experience programming in languages like Java, Python, and C#. These are what we call high-level programming languages. A high-level programming language is easier to understand by programmers. Low-level programming languages like assembly and binary code are interpreted by a computer, and much harder for human programmers to understand. C++ sits in between these sets of high-level and low-level languages, and is referred to as a middle-level programming language. It contains powerful high-level programming features like object-oriented programming, but also allows the programmer to directly manage the memory of the program, something typically offered by low-level languages. It is for this reason that we call C++ a middle-level language, as it offers a mix of features from high and low-level programming languages. C++ was created by Bjorn Strostrup in 1979. It is based in C programming, but features classes, an object-oriented feature not supported in C. Before it was called C++, its working title was C with classes. It is a case-sensitive language, so the difference between capital and lowercase letters is important when coding in C++. C++ is object-oriented, fast, portable, and widely used. C++ is an object-oriented language, meaning it gives us the ability to create classes that serve as the blueprints for creating objects. It supports the 4 pillars of object-oriented programming, or OOP, which are inheritance, encapsulation, abstraction, and polymorphism. If these concepts are unfamiliar to you, don't worry. We'll be doing a deep dive on OOP later in the course. It is also faster than many other programming languages. In fact, it is one of the most efficient and fastest programming languages that you can use. One of the features that makes the execution speed of C++ so impressive is that it is statically typed, meaning that type checking is performed when the code is compiled, instead of when the program is run. C++ is portable. When we refer to a programming language as portable, we mean that it can be used on a variety of platforms and operating systems. It is not tied to one OS. This allows us to move software from one machine platform to another, without having to do a major refactor of the program. It is one of the most widely used languages. All of the major operating systems, Windows, Mac, and Linux, are programmed in C++. It is frequently used in finance and banking applications, since these process very high numbers of transactions each day. This powerful programming language is used across industries, and is the backbone of the majority of the software we use on a daily basis. If you want to become a professional programmer and make a great salary, one of the best languages you can learn is C++. Trust me, knowing this language will greatly improve your resume and employability. In this video, we will go over the solution and explanation to the coding exercise that we just did. The question asks us to write a program that outputs the string hello world to the C++ console. Up at the top of the code, we need to include the IOStream header file, since this will give us access to the standard output stream, cout. Inside of the hello world function, we will type std, then 2 colons, and then cout. After that comes 2 less than signs for the put2 operator, and then the string hello world. It is important to make sure that the H and W are capitalized, and that there is an exclamation mark at the end, just like the question shows us, since strings are case sensitive. At the end of the line comes a semicolon. When we run the code to check our solution, notice that it is correct. In this video, we will take a look at the history of the C++ programming language. In 1979, the development of a project called C with Classes began at Bell Labs by a gentleman named Bjorn Strostrup. This project was eventually renamed C++, and the first version of C++ was released in 1985. 1998 marked a key milestone in C++ history for 2 reasons. A new version of C++ was released, C++ 98, and the ISO began standardizing C++. Each C++ version has the last 2 digits of the year it was released. In 2003, C++ 03 was released. This was followed by C++ 11 in 2011, and after that, a new version of C++ has been released every 3 years. It was followed by C++ 14, C++ 17, and most recently C++ 20 in 2020. The next version of C++ is slated to be released in 2023. In this video, we will learn how to run C++ code from the terminal on Mac. We can actually do this from directly inside of the Visual Studio Code IDE. Sometimes, like in the case where you want to obtain user input, you need to run your code from the terminal as opposed to just looking at the output in the debug console. Let's be sure that our file is saved. The first step is to click the key combination Ctrl-Shift-tilde, which is the upper left character on the keyboard with the squiggly line. This will open up the terminal window in VS Code. Next, we need to compile the file, which we can do with the make command, then a space, and then the name of our file without the CPP file extension. So in my case, I have typed make example. When we hit enter, the code in our file will be compiled. The next step is to actually run the program. To do this, we can type a dot, then a /, and then the name of the file without the CPP file extension. So I will type ./example. When we hit enter, notice that the program was run, and the output from our program was displayed in the terminal. In this video, we will learn how to run our C++ code from the terminal on Windows. To do this, we simply need to configure a setting within the Visual Studio Code editor itself. Let's go to File, Preferences, Settings. On the left-hand side, be sure to click Extensions, and then Run Code Configuration. One of the checkboxes here, which is unchecked by default, is Run in Terminal. If we toggle this checkbox, the C++ code we run in Visual Studio Code will automatically run in the integrated terminal in the IDE, which is something we will need when we take in user input in Section 3 of the course. Let's recap what we learned in this section of the course. First, we installed and set up Visual Studio, the IDE that we will use to write C++ code. Then we learned how to create a C++ file, which is a file with a .cpp file extension. Next, we wrote our first C++ program, Hello World. After that, we got a look at some of the key features of C++. Next came a coding exercise, which tested our ability to code a Hello World program in C++ to ensure that you retained the knowledge taught so far. After each coding exercise in this course is a video containing the answer to it and explaining the solution step by step. Next, we learned about the history of C++, some of the key milestones of the language over the years. Finally, we learned how to run C++ code from the command line. In this section, we will learn the basics of C++. First, we will look at how a C++ program is run. Then we will learn about include, a programming construct we use to import header files into our C++ programs. After that, we will learn more about C++'s main function. Then we will learn about cout and the put2 operator and the role that they play in C++ programming. Next, we will look at the various built-in types that the language gives us access to. After that, we will take a deeper look at the Boolean data type in C++. Next, we will learn about characters in C++. Then we will learn about integers in C++. After that, we will learn about the floating point types that C++ supports, like floats and doubles. Next, we will learn about the various arithmetic operators in the C++ programming language. Then we will learn about the order of evaluation that applies to C++ expressions and how they are evaluated. After that, we will learn about the different comparison operators that C++ supports. Next, we will learn about the role of the const keyword in C++ programming. After that, we will take a look at the string data type, and then practice working with strings in a coding exercise. Next, we will look at the answer and explanation to that coding exercise. Then we will review some key takeaways for this Basics of C++ section of the course. After that comes the quiz for this section, and finally a review of the answers to the quiz and the explanations for the correct answers. In this video, we will learn how a C++ program is run. In other words, what happens under the hood when we run the code. When you're learning a programming language, understanding what happens when it is run can help put the code you write in perspective of the larger picture. That code being a piece of the broader program. Firstly, it is worth mentioning that C++ is a compiled language and is statically typed. What does this mean? In computer programming, there are two types of languages, compiled languages and interpreted languages. Let's take a look at a real-world analogy for what these mean. If there is a book that is in another language, one you are not familiar with, there are two ways for you to understand the information in the book. One is to get a copy translated into the language you understand. The other would be to have someone that speaks both languages, the one that you speak and the one the book is in, read the book to you line by line. A compiled language is like the first scenario. It gets converted directly into machine code, which the computer understands and can execute. An interpreted language is different. It gets run through a program called an interpreter that translates it into machine code line by line. The fact that C++ is a compiled language means that when we run the code, it gets compiled into machine code that is directly executed on the machine and does not need an interpreter, the middleman, so to speak. Statically typed means that C++ variables are of a specific type. If you've ever written Python code, you may be familiar with the concept of being able to assign a variable any value in the program. For example, a variable holding an integer could later hold a bool, etc. For this reason, we call Python a dynamically typed language. C++, in contrast, is statically typed. Now, let's understand what happens under the hood when a C++ program is run. The code that we are writing is referred to as source code. Each file of code that we write needs to get compiled, which means it gets translated into machine code, aka an object file. Since a program usually consists of multiple files, each of these becomes a separate object file. The object files then get put through a linker, which combines them into a single executable file that can be run by the machine. In this video, we will learn about the include preprocessor directive. C++ features something called preprocessor directives. These are instructions that the compiler will take into account before doing the actual compiling. We know that something is a preprocessor directive if it has a hashtag in front of it. For example, hashtag include is a preprocessor directive that is used for file inclusion, including code from one file in another. The name of the file to include comes inside of a pair of angular brackets. For example, typing the include preprocessor directive and then iostream inside of angular brackets imports the iostream header file into our code, giving us access to the standard input and output stream amongst many other things. Another key call out here is that there are two types of files that can be included in your C++ programs in this fashion. Some are standard files like iostream that are predefined for the language and we use to access standard functionality. We can also import files that are user-defined, that is, files which we wrote C++ code in that we want to reuse in another file. Programming in this way allows us to write more modular code and saves us from having to type the same function multiple times. In this video, we will learn about C++'s main function. The main function is the starting point for a program to execute. C++ programs can be made up of many files, functions, and lines of code, and it is important that the computer is clear on where to start when executing the program. In its most basic form, the main function in C++ looks like this. It is important to note that the main function of a C++ program will always have a return type of int. You may also see the main function taking in arguments, like this. When the main function has these arguments, it is so that they can be supplied when the program is run via the command line. As such, we call them command line arguments. argc and argv are the traditional names for these arguments, but you can name them whatever you want. I encourage you to stick to this convention though, so that your code is more easily read and understood by other programmers. The integer argument, typically named argc, is an integer that is greater than or equal to 1. It is the length of the array passed in as the second argument. The body of the main function goes inside of the curly braces. In this video, we will learn about the standard output stream and the insertion operator. Cout is the standard output stream and is a part of the iostream header file in the standard library. To output to the console, we use the insertion operator along with cout. For example, we can use cout, which we need to prefix with std::. Next comes the insertion operator, which is two opening angular brackets. Then, on the right hand side goes the string we want to output to the console, for example, ABC. Running the code will display the string ABC in the C++ console. Another thing to note is that we can chain multiple insertion operators when outputting information to the standard output stream. Building on the code that we currently have, we can add another insertion operator, and then the string 123. Now, when we run the code, notice that ABC123 is printed to the console. We can use the new line character \n in order to separate this output onto two lines. Let's add another insertion operator and then the new line character so that it is sandwiched between the other two strings. When we run the code, notice that ABC is on the first line and 123 is on the second line. In this video, we will learn about the fundamental, built-in data types that C++ supports. There are four built-in types provided by C++: Booleans, characters, integers, and floating point numbers. A Boolean can have one of two values, true or false. Booleans are particularly useful to determine which branch of code to execute, which we will learn about in more detail soon when we learn about control flow statements like if, else statements in C++. For example, we can create a Boolean variable named b1, initialized to a value of true. A character is one character inside of single quotes. A char is 1 byte or 8 bits of data. For example, we can have a variable of type char named c1 that we set equal to the character value a. An integer in programming is the same thing as an integer in mathematics. It is a positive or negative whole number, or 0. For example, we can have an int variable named num1 that we assign a value of 5. There are two main types of floating point numbers, floats and doubles. Floating point numbers have a decimal point in them. For example, we could have a variable of type float named float1 that we set equal to a value of 2.0f. Note the lowercase f at the end of the number. This signifies that it is a float. A double is called a double because it can store twice as much, or double the value, as a float can. For example, we can create a variable of type double named double1 that we set to a value of 2.0. Note that with doubles, we don't put an f at the end. Now that we've seen an example of each of the built-in types that C++ provides us, we will take a deeper look at each of them in the coming videos. In this video, we will take a deeper look at the built-in bool data type that C++ gives us. To create a Boolean variable, we specify a type of bool. For example, let's create a variable of type bool named yes that we set equal to a value of true. Then we will output the value of yes to the console by typing std:" cout, then the insertion operator, and then yes. When we run the code, notice that 1 was output. It is important to note when printing out a Boolean value to this standard output stream, a value of true will be output as 1, which is the equivalent of true. Next, let's look at an example where we create a bool named no that we assign a value of false. After that, we will output the value of no to this standard output stream. When we run the code, notice that a value of 0 was printed out. 0 is the equivalent of false in a computer program. The relationship between integers and booleans goes beyond these examples. For example, we can create a variable of type bool named 5 that we set equal to an integer value of 5. Next, we will output 5 is, and then the value of 5 to the console. When we run the code, notice that 5 is 1 was output to the console. This can be read as 5 is true. Any number that isn't 0 results in a Boolean value of true. Another example we could look at is if we have a Boolean variable named 0, assigned an integer value of 0. Then we will output 0 is, and then the value of 0 to the console. When we run the code, Notice that the statement 0 is 0 is output to the console. Knowing that the value 0 represents false in a computer program, we can read this statement as 0 is false. In this video, we will take a look at C++'s built-in character data type. To create a character, we specify the char type. For example, we can create a char variable named letter that we set equal to the letter A inside of single quotes. When we have one letter inside of single quotes, it is what we refer to as a character. Another example of a character variable would be a char named grade that we assign a value of B inside of single quotes. We can also create multiple character variables on one line, separated by commas. For example, we can create a char variable A set equal to A, then a comma, B set equal to B, then a comma, C set equal to C. This line of code creates three character variables A, B, and C, and sets them equal to their respective character values. Aside from these examples of characters, there are also escape sequences that have special meanings in C++. An escape sequence goes inside of single quotes, then comes a backslash, and then a character. Here's a list of the different character escape sequences. One example is the new line character. To see an example of this escape sequence in action, let's output to the console our variable A, then the new line character, then the variable B. When we run the code, notice that the character A is output to the console, and then the character B is output on the line after that, thanks to the new line character that we utilized. Another escape sequence is the horizontal tab. For example, we can output a tab, and then the characters A, B, and C to the console. When we run the code, notice that A, B, and C are indented with a horizontal tab. In this video, we will learn about the integer data type in C++. An integer in C++ is analogous to an integer in mathematics. It is defined as a positive or negative whole number, or 0. Integer variables have a type of int specified. For example, we can have an int variable named positive that we assign a value of 1. We can also have an int variable named 0 set to a value of 0. Another example of an integer would be an int variable named negative, assigned a value of -1. In a couple of lectures, we will take another look at integers when we learn about arithmetic operators in C++. In this video, we will learn about floating point numbers. A floating point number has a decimal point in the value. There are two types of floating point numbers in C++, floats and doubles. Let's look at some examples of floats first. For example, we will create a float variable named f1 that we set equal to 2.0f. Note that float variables have a suffix of a lowercase f. Another example of a float would be a variable named f2 that we set equal to 2.5f. We can also have a float variable named f3 that we set equal to 2e minus 4f. This represents the number 2 times 10 to the -4th. Next, let's look at some examples of doubles. For example, we can create a variable of type double named d1 that we set equal to 6.0. Notice that a double does not have any suffix, whereas floats have the lowercase f at the end. Another example of a double would be if we have a variable named d2 that we set equal to 7.5. Also, we could have a variable of type double named d3 that we set equal to 8e minus 3, which corresponds to a value of 8 times 10 to the -3rd. Let's look at the differences between floats and doubles. Floats and doubles are very similar, and both have decimal points in the values. A float has a size of 4 bytes, and a double, as the name would imply, has a size of 8 bytes. A float has a precision of 7 decimal places, and a double has a precision of 15 decimal places. A potential problem that we need to look out for is the potential loss of information when converting a double to a float. For example, let's create a variable of type float named double to float, which we set equal to 2.123456789. Then we will output double to float to the console. When we run the code, notice that a few of the decimal values at the end were lost. This is because a float cannot hold as many decimal point values as a double can. We can also specify the number of decimal places that can be output to the console. For example, let's go to the top of the code and include iomanip. To set the precision that can be output to the console, we can utilize the setPrecision function. Let's use this setPrecision function and pass in a value of 3. Note that this function is exclusive, so it will set the precision to 2, not 3. When we run the code, notice that only 2 decimal places were output. In this video, we will learn about arithmetic operators. One is the subtraction operator. For example, let's output the string 3 minus 1 to the console, and then the result of 3 minus 1. When we run the code, notice that 3 minus 1 equals 2 was output to the console. Another arithmetic operator C++ gives us access to is the addition operator. For example, we can output the string 5 plus 2 equals, and then write the value of 5 plus 2 to the console. When we run the code, notice that 5 plus 2 equals 7 was printed out. To divide two numbers using C++ code, we can use a /, which functions as the division operator. For example, we can output the result of 10 divided by 2 to the console. When we run the code, notice that the output is 5. Next, we will learn how to multiply numbers in C++. We can use the asterisk, aka the multiplication operator, to obtain the product of 2 or more numbers. For example, we can multiply 4 by 4. When we run the code, notice that this operation results in a value of 16 being output to the console. We can utilize the modulus operator to obtain the remainder when one number is divided by another number. The remainder is the amount left over after the division takes place. For example, 4 modulus 2 results in a value of 0. This makes sense because 2 goes into 4 2 times with a remainder of 0. Another example of the modulus operator would be 5 modulus 2. In this case, notice that when we run the code, the result is 1. 2 goes into 5 2 times with a remainder of 1 left over. Let's take a look at another arithmetic operator in C++, the increment operator. First, we will create an integer variable named 1 that we assign a value of 1. Then we will output the result of 1 plus plus to the console. The plus plus operator is the increment operator and will increase the value of a variable by 1. However, when we run the code, notice that 1 was output. Why is this? We utilized the postfix increment operator, so the addition happens after the number is output to the console. Let's instead utilize the prefix increment operator and output the result of plus plus 1 to the console. When we move the plus plus in front of the variable name, it is referred to as prefix instead of postfix. Notice that when we run the code, 2 is output to the console. There is also a decrement operator, which is minus minus. Let's create an int variable named 5 that we assign an integer value of 5. Then we will output 5 minus minus to the console. When we run the code, notice that 5 was output to the console. This is again because we used it as a postfix operator instead of a prefix operator, so that the subtraction happened after the value was output to the console. If we move the minus minus in front of the variable name and then rerun the code, notice that 4 was output to the console. In this video, we will learn about the order of evaluation for the arithmetic operators that we learned about in the last lecture. Before we dive into the technical details, let's take a look at a math example. Pretend you're back in high school algebra class and solve the following problem. 2 plus 5 times 3, but no cheating, no computer or calculator. You can do this in your head or using a pen and paper. Did you come up with a value of 21? If so, believe it or not, your answer is incorrect. The correct answer is 17. This is because of the order of operations, otherwise known as PEMDAS, short for parentheses, exponents, multiplication, division, addition, subtraction. The multiplication of the 5 times 3 happens first, and then the 2 gets added. We can verify this by outputting the result of the expression 2 plus 5 times 3 to the console. When we run the code, notice that 17 was output. If we want the addition to occur first, we can put the 2 plus 5 part inside of parentheses to force it to evaluate first. When we run the code, notice that we get 21 since 5 plus 2 is equal to 7, and then 7 times 3 is 21. Here's a chart showing the arithmetic operators in C++ and the order that they're evaluated in. Operators at the top of this chart get evaluated first, and ones at the bottom get evaluated last. The postfix increment and decrement operators get evaluated first. Then comes the prefix increment and decrement operators. After that come the multiplication, division, and modulus operators. Next come the addition and subtraction operators. Finally come the plus equals, minus equals, times equals, divide equals, and modulus equals operators. In this video, we will learn about the comparison operators provided by C++. The role of a comparison operator, as the name implies, is to compare two things. Let's look at an example. We will create an integer variable named x that we set equal to a value of 6. After that, we will have an int variable y assigned a value of 6. Then we will create a Boolean variable named are they equal that we set equal to x, then two equal signs, and then y. The double equals operator here checks if two things are equal. In this case, it is checking if x and y are equal. Finally, let's print out the value of are they equal to the console. When we run the code, notice that 1, aka true, was printed out. This is because both x and y are currently set to a value of 6, so they are in fact equal. If we change the value of y to 3 and then rerun the code, notice that 0, aka false, was output. This is because the values that x and y are storing are not equal. The not equals operator is represented by an exclamation point followed by an equal sign. It will return true if two values are not equal, and false if they are equal. As such, this is the opposite operator to the double equal sign we just looked at. Let's look at an example of using the not equals operator. We will output the result of 6 does not equal 3 to the console. It is important to note that we need to surround the expression in parentheses here. When we run the code, notice that 1 was output to the console, since 6 is not equal to 3. Another comparison operator is the greater than operator. Instead of checking if 6 is not equal to 3, let's change the expression to check if 6 is greater than 3. When we run the code, notice that 1, aka true, was output to the console. Here is a list of the comparison operators supported by C++. Equal to checks if the two values are equal. Not equal to checks if two values are not equal. Less than checks if one value is less than another value. Less than or equal to checks if one value is less than or equal to another value. Greater than checks if one value is greater than another value. Greater than or equal to checks if one value is greater than or equal to another value. The true power of comparison operators lies in using them to control branching code logic, which is something we will learn about in the next section with conditional statements. Before that, though, there are a few more basics of C++ that I want to go over. In this video, we will learn about constants in C++. The const keyword is used to specify a variable as a constant. If a variable is marked as constant, this essentially means that the value of the variable cannot be changed. For example, we can create a const int variable named x that we assign a value of 1. This tells the program that x is always going to have a value of 1, and its value will never change. If we attempt to set x to 3 and then run the code, notice that there is a compile time error. This is because we have used the const keyword when assigning x a value of 1, so we cannot change its value after that. Another error to watch out for when creating constant variables using C++ is if you create a constant variable, but don't assign it a value on the line where you create it. For example, let's create a const int y. If we run the code, notice that we get an error at compile time since we didn't assign y a value. In this video, we will learn about strings in C++. A string is text inside of double quotes. To access the string class, we need to import it by using the include preprocessor directive and typing string inside of angular brackets. To save us from having to type std::: in front of the references we make to classes from the standard library, we can type using namespace std. Let's look at how we can create a string using C++ code and how we can work with strings. For example, we will have a string variable named s that we set equal to the string hello world. Strings are essentially text inside of double quotes. Let's output s to the console. When we run the code, notice that hello world was output. We can obtain the length of a string by using the size function. For example, let's create an int variable named length, which we set to s.size. Then we will output length to the console. When we run the code, notice that 11 is printed. This makes sense since the string hello world is 11 characters long. Note that the space in between the words hello and world counts as a character. One important concept when working with strings is called indexing. Each character in a string is assigned an index that represents its position. Indexing starts at 0. This means that the first character in the string is at index 0. The second character is at index 1. The third character is at index 2, so on and so forth. To illustrate this, we can output the character at index 0 to the console. Note the syntax here. The position or index goes inside of square brackets. When we run the code, notice that h was printed to the console. If we specify an index of 1 and then run the code, notice that e was output to the console. This makes sense, since the index of the character e in the string s is 1. Utilizing indexing allows us to do much more than just obtain the value of the character at that index. We can also change its value. For example, let's set the character at index 0 equal to lowercase h. If we output s to the console, notice that the first letter is a lowercase h instead of a capital one. We can also perform slicing of a string, which means grabbing a part of the string, also known as a substring. To do this, we can use the substring function. For example, let's output s.substring and pass in 0 as the first argument, which represents the starting position, and 5 as the second argument, which represents the ending position. One important callout here is that the end position is exclusive, meaning that the end position will go up to, but not including the number specified. So the substring will consist of characters at indices 0 through 4. When we run the code, notice that hello was output to the console. This makes sense since h has an index of 0, e has an index of 1, l has an index of 2, l has an index of 3, and o has an index of 4. Another example of slicing a substring would be if we pass in a value of 6. When we only specify one argument to the substring function, it is the start position, and the substring will go to the end of the string. Notice that when we run the code, world was output to the console. Strings are an incredibly important data structure in computer programming, so it is important to understand how to work with them when coding in C++. This coding exercise presents the situation that there are two types of objects, joules and stones, and asks us to find the number of characters in the string joules that are also present in the string stones. One way to solve this problem is to go through each character in joules and each character in stones and check if the two are equal. We will keep track of each time that they are equal and then return that count at the end. Let's start by creating an int variable named result and initializing it to a value of 0. Next, we will have a for loop which will be responsible for iterating over each character in the joule string. To do this, we can begin the for loop at int I equals 0, run it while I is less than joules.size, and increment I by a value of 1 each time. Then we will iterate over each character in the string stones, which we can do using a second for loop. This type of technique, having a for loop inside of another for loop, is often referred to as a double for loop or nested for loop. This inner for loop will start at int j equals 0, run while j is less than stones.size, and increment j by 1 after each iteration. Inside of here we will check if joules at index I is equal to stones at index j, and if so we will increment result. At the bottom of our function, outside of the loops, we will return result. When we run the code to check it, notice that it is correct. Let's recap the key takeaways from this section of the course. We learned how a C++ program is run, namely that the source code we write is compiled into object files, which are then put through a linker and packaged into an executable file. We also looked at the include preprocessor directive, which allows us to import code that we can use in our C++ program. The main function is the entry point when running a C++ program, and it is important to understand that you have to have a main function in your program so that the code knows where to start executing. In C++, cout is the standard output stream and enables us to output information to the console. The insertion operator can be used to put information in cout. There are 4 main built-in types provided by the C++ programming language, which are Booleans, characters, integers, and floating point numbers. A Boolean is a variable that can be one of 2 values, true or false. A character is one character of text inside of single quotes. An integer is a positive or negative whole number, or 0. And a floating point number, like a floatdouble, has a decimal point in its value. C++ provides us arithmetic operators that we can use to perform mathematical operations on numbers. When using these operators, it is important to understand the order of their evaluation. Comparison operators allow us to compare 2 values. A constant is a variable marked with the const keyword, and the value of a constant cannot be changed at any point in the program. Strings are text inside of double quotes. We can work with strings in C++ by including the string header file at the top of the program. Indexing is when we refer to a character in a string by its position, or index. Slicing a string into a substring is when we take a sequence of characters from that string by specifying a start and end position within the bounds of the string. In this video, we will look at the answers to the quiz from this section. The first question asks us which of the following is a float. The answer is 9.0f. Recall that a float in C++ meets 2 main criteria. It has a decimal point in the value and a lowercase f right after. 2 is an integer. 3.5 is a double, since it does not have a suffix of a lowercase f. Negative 100 is an integer, since it is a negative whole number. The second question provides us the string coding, and asks us which character is at index 2 in the string. The correct answer here is D. Indexing in C++ starts at 0, so C has an index of 0, O has an index of 1, and D has an index of 2, making D the correct answer. In this section of the course, we will learn about input, conditional statements, and loops. By the end of this section, you will have an understanding of obtaining and responding to user input, controlling the flow of execution of the code with conditional statements, and using loops to execute code multiple times. First, we will learn about cin and the extraction operator. Then we will learn about if, else statements. After that will come a coding exercise testing our knowledge of if, else statements, which will be followed by a video explaining the solution to the coding exercise. Next, we will learn about switch statements. After that will come a coding exercise on switch statements, and then an answer and explanation video for that coding exercise. Then we will learn about for loops, and then test our understanding of the topic with a coding exercise, which will be followed by a video explaining the solution to the coding exercise. After that, we will learn about while loops, and in a similar fashion we will complete a coding exercise, and then take a look at the solution to it in the subsequent video. A variation of the while loop is the do while loop, which we will learn about next. Then we will learn about goto. After that, we will learn about pointers. Next, we will learn about arrays, and then test our knowledge with a coding exercise on the topic. Then we will learn about vectors, and then test our knowledge with a coding exercise. At the end of this section, we will look at key takeaways from what we learned, take a quiz to test our knowledge, and then go over the answers and explanations to the quiz questions. In this video, we will learn about the standard input stream and the extraction operator. Essentially, these allow us to obtain input from the user. For this first example, we will prompt the user to enter their name and store the value that they enter in a variable. At the top of the program, we need to include the string header file. Let's create a string variable called name that we initialize to an empty string. After that, we will output the string enter your name to the console. After that, we will type cin and then 2 closing angular brackets. Cin is the standard input stream. It is essentially the opposite of cout. The 2 closing angular brackets are referred to as the extraction operator and are used along with cin to obtain user input. We want to store what the user types in the name variable, so we will type name. Finally, we will output the string you entered and then the value of the name variable to the console. In order to be able to input a value into the code when it is run, we need to run it from the terminal. To do this, we can press Ctrl-Shift and the upper left key on the keyboard with the squiggly line and accent mark. From there, we type make and then the name of the file. In my case, that is example. Then we will hit the enter key to run the command. This will compile the file. Finally, we will run the code by typing // and then the name of the file. When we run the code, notice that we are prompted to enter our name, and when we input something and hit enter, the program tells us the name that we entered. For the next example, we will create an int variable named number that we assign an initial value of 0. Then we will prompt the user to enter a number. After that, we will store the value that the user inputs into the number variable. Then we will output the string number doubled is, followed by number times 2 to the console. Let's save the file. Then we will open up the terminal with the hotkey combo we learned earlier. Next, we will run the make command on our file, and then the run command. When we run the code, notice that we can type a number, and then when we hit enter, the number that we typed in is doubled. In this video, we will learn about if, else statements in C++. These programming constructs allow us to write branching code that will execute a different set of instructions based on the value of one or more conditions. We'll start out looking at an if statement and then build on that example. Let's create a Boolean variable named condition, which we assign a value of true. To use an if statement, we type the word if, then put the condition we want to check in parentheses. A pair of curly braces comes next, and inside of here goes what we call the body of the if statement, the code that we want to be run if the condition for the if statement evaluates to true. Let's output the string condition was true to the console. When we run the code, notice that condition was true was output to the console. This makes sense since the condition variable we are checking with the if statement does have a value of true. Let's change the condition to false and then run the code again. Notice that nothing was output to the console this time. Since the condition we are checking for the if statement is false, the code inside of the body of that if statement was not run. An if statement can be paired with something called an else statement, which will execute in the event that the if statement above it evaluates to false. Let's add an else statement below the if statement that we currently have in our code, and inside of the body of the else statement we will output condition was false to the console. When we run the code, notice that condition was false was output to the console. Next, we will create an integer variable named x and assign it a value of 4. Along with if and else statements, there is another type of statement called else if. An else if statement comes after an if statement but before the else statement, and is used to check an alternative condition. For example, let's create an else if statement that checks if our variable x is holding a value of 4. If that is the case, we will output x is 4 to the console. When we run the code, notice that x is 4 was output to the console. One important thing to note here is that the code inside of the else statement was not executed. Out of the if, else code block, only one of the statements will be executed, whichever one comes first and whose condition evaluates to true. If we change the condition to be if x does not equal 4 and then run the code again, notice that the code inside of the else statement was executed, since both the if and else if statements were not hit, since their conditions evaluated to false, leaving the else statement code to be executed. One thing I want to make clear is that you can have multiple else if statements tied to the same code block. Up at the top of the code we will include the string header file so that we can utilize the string class for this next example. For example, let's create a variable of type string named s and assign it a value of the string abc. Then we will add another else if statement that checks if s is equal to the string value abc. Inside of here we will output s equals abc to the console. One callout I want to make is since we are nesting double quotes inside of a string, we need to prefix the inner double quotes with backslashes, the escape character that we learned about in the last section. When we run the code, notice that s equals abc was output to the console, thanks to this new else if statement that we added. Since the conditions of the if and else if statements above it evaluate to false, and the condition of this else if statement evaluates to true, its body of code is run. In this video, we will go over the answer and explanation to the coding exercise we just did. The problem starts us off with a float variable named f, assigned a value of 2.0f. We are asked to write an if statement that outputs the string correct to the console if f has a value of 2.0f. To solve this question, we use an if statement, and inside of there check if f is equal to 2.0f. If so, we output the string correct to the console. When we run the code to check our solution, notice that it is correct. In this video, we will learn about switch statements in C++. A switch statement is another type of conditional statement that allows us to control the flow of program execution. For this example, let's start off with an int variable x that we assign a value of 2. Next, we type the word switch. Inside of a pair of parentheses goes the condition we want to check, which in this case will be the value of x. In the case that x is 1, we will output x is 1 to the console, and then break from the switch statement. In the case that x is 2, we will output x is 2 to the console, and then break from the switch statement. Note that each of these is called a case statement, and at the end of each we need to use the break keyword to exit from the switch statement. When we run the code, notice that x is 2 is output to the console, since the variable x is holding a value of 2. For this next example, let's change the value of x to 5. Similar to how an else statement functions in an if, else code block, we can use the default keyword at the bottom of a switch statement, which will be executed if none of the case statements above it were hit. Let's add a default at the bottom of our switch statement that will print out default code hit to the console, and then break from the switch statement. When we run the code, notice that default code hit was output to the console. In this video, we will go over the answer and explanation of the coding exercise that we just completed. The problem starts us off with an integer variable named x, assigned a value of 1. We are asked to write a switch statement that outputs x is 1 to the console if x has a value of 1. Let's create a switch statement that checks the value of x. Inside of the body of the switch statement, we will have a case checking if x is equal to 1. If that is the case, we will output the string x is 1 to the console, and then break from the switch statement. When we run the code to check it, notice that it is correct. In this video, we will learn about for loops in C++. A for loop allows us to execute code repeatedly. Let's write out our first for loop, and then I will explain it step by step. We will create a for loop that starts out at int I equals 0, runs while I is less than 5, and increments I by 1 each time. Inside of the for loop, we will output I, and then a space to the console. Okay, before we run this code, let's break it down. The first part of the for loop is the start value. I less than 5 is the stop value, meaning that this for loop will run while the value of I is less than 5. And the third part of the for loop is the step value, how much we want to change I by each iteration of the for loop. When we run the code, notice that the for loop is run when I has a value of 0, 1, 2, 3, and 4. In this last example, we looked at a for loop that starts out with I at a low value and increases I on each iteration. In contrast, we can have a for loop that starts with I at a large value and decrements I down to a smaller value each iteration. Let's create a for loop that starts integer I at a value of 3, runs while I is greater than 0, and decrements I by 1 each time. Inside of the for loop, we will output the value of I and then a space to the console. When we run the code, notice that 3, 2, and 1 were output to the console. 0 was not output since this for loop stops executing when I stops being greater than 0. Another important use of for loops is iterating over a sequence of values. Recall that a string is a sequence of characters. This next example will make use of strings, so let's include the string header file at the top of the program. Let's create a string variable s that we assign a value of the string abcd. Then we will have a for loop that starts at int I equals 0, runs while I is less than s.length, and increments I by 1 each time. Inside of this for loop, we will output the value of s at index I to the console. When we run the code, notice that each of the letters A, B, C, and D in the string were output to the console. It is also possible to nest for loops in C++, in other words, to have a for loop inside of another for loop. For this example, let's create a for loop that starts at int I equals 0, runs while I is less than 3, and increments I by a value of 1 each time. Inside of this for loop, we will output a new line, then the string I equals, and then the value of I, then a new line, and then a tab to the console. Inside of this for loop, we will have another for loop that starts at int j equals 0, runs while j is less than 3, and increments j by a value of 1 each iteration. Inside of this for loop, we will output j equals, then the value of j, and then a space to the console. When we run the code, notice that the outer for loop gets executed, making I 0, and then the inner for loop executes. The outer for loop does not resume to set I to a value of 1 until the inner for loop has completed its iterations. This is the behavior of nested for loops in C++. In this video, we will go over the answer and explanation to the coding exercise that we just did. We are given a string variable named s assigned a string value of hello, and tasked with writing a for loop that iterates over each character in string s, and prints it on a new line. Let's create a for loop that starts out at int I equals 0, runs while I is less than s.length, and increments I by a value of 1 each time. Inside of this for loop, we will output the character at index I in string s to the console, followed by a new line character since the problem instructs us to output each character on a new line. When we run the code to check it, notice that our solution is correct. In this video, we will learn about while loops in C++. A while loop allows us to run code multiple times. We should use a for loop when we know the amount of times we want to loop through the code, and a while loop when we aren't sure how many times to loop through. A while loop will execute while its condition is true. Let's create an int variable x that we assign a value of 2. While x is greater than 0, we will output x and then a new line to the console. After that, we will decrement x. When we run the code, notice that x was output with a value of 2 and then a value of 1. The code stopped executing once x held a value of 0 because the condition for the while loop became false. Let's look at another example of a while loop. For this example, we will create a Boolean variable named condition that we assign a value of true. While condition is true, we will output hello world to the console. Then we will set condition to false. When we run the code, notice that hello world was output to the console. In both examples that we just looked at, it is important to note that the condition of the while loop became false. Beware a while loop whose condition never changes to false, as this causes something called an infinite loop, which executes indefinitely, and causes the program to crash. For example, you never want to have true as the condition, unless you have code that will break out of the while loop inside of it. In this video, we will go over the answer and explanation to the coding exercise that we just completed. The problem asks us to write a while loop that executes while num is greater than 4, outputs the value of num to the console each iteration, and decrements the value of num on each iteration. It starts us off with an int variable num, initialized to a value of 8. Let's create a while loop that executes while num is greater than 4. Inside of here, we will output num to the console. Then we will decrement the value of num using the minus operator. When we run the code to check our solution, notice that it is correct. In this video, we will learn about do-while loops. A do-while loop is a variation of the while loop that we learned about. The syntax looks like this. First comes the word do, then the code we want to do inside of curly braces, while the condition inside of the parentheses is true, and finally a semicolon. Oftentimes you will see it formatted like this with the code inside of the body of do on a separate line and the while condition part on another line. For example, let's create an int variable named num that we assign a value of 0. Then we will have a do-while loop. Inside of the do part we will output num to the console, followed by a new line. After that we will increment num. For the while part we will specify a condition of num less than 2. In other words, while num is less than 2 we will execute the body of the do statement. When we run the code, notice that the values 0 and 1 are output to the console. One important callout here, and difference from the traditional while loop, is that the code inside of the do part will always be called at least once, even if the condition is false. For example, if we change the condition of the while loop to false, and then run the code, notice that 0 was still output to the console. In this video, we will learn about using goto statements in C++. Before I jump into teaching this programming construct, I want to mention that it is usually advised to try not to use goto statements, since they can make tracing the flow of execution of the program hard to follow. A goto statement is a way to jump to a labeled spot in the code and execute it. A label is an identifier followed by a colon. Let's look at an example of the goto statement in action. We will use the goto keyword and jump to the first label, a label we have not created yet. Let's create a label named third, and after the colon we will output the string third to the console, and then return 0 to terminate the execution of C++'s main function. After that we will have a label named second, and after the colon we will output second, then a space to the console, and then use the goto keyword to jump to the third label. Next we will create a label named first, and output the string first to the console, and then a space, and then use the goto keyword to jump to the second label. Notice that this code is basically backwards, going third to second to first, but thanks to using the goto statement this doesn't matter. When we run the code, notice that first, then second, and finally third was output to the console. Upon hitting the goto first code, it jumps to the first label and executes its code. It then hits goto second and jumps to the second label's code. When it hits goto third, it jumps to executing the code for the third label. Then it hits return 0 and terminates the main function. In this video, we will learn about pointers. A pointer is a variable that stores the memory address of another variable. Before we learn about pointers, let's take a look at how we can obtain the memory address that a variable is stored at. We will create an int variable named I, assigned an initial value of 3. Then we will output ampersand I to the console. When we run the code, notice that its memory address is printed out. It will almost certainly be different than the one you see on my screen, and if you run the code multiple times, you will get a different address each time. Don't worry. This is normal. As I mentioned, a pointer is a variable that stores the memory address of another variable in the C++ program. Up at the top of the code, let's include the string header file. Let's create a string variable named s that we assign a value of the string abc. Then we will type string, then an asterisk, and then the name of the variable, which we will call pointer, and set it equal to ampersand s. Finally, we will output pointer to the console. When we run the code, notice that the memory address being stored by the variable was output to the console. Let's break down the syntax of creating a pointer. The pointer needs to have the same type as the variable it is pointing to. Then comes an asterisk, the name of the pointer, and then we set it equal to ampersand, and then the name of the variable of interest. The recommended syntax for a pointer is to have the asterisk immediately after the type, but it is also valid to have it before the variable name, or in between the type and variable name. All of these ways are valid, but the first way we looked at is the recommended approach. In this video, we will learn about arrays in C++. An array stores a sequence of values. For example, we could have an int array named nums that we set to the values 1, 2, 3, and 4. Note that it is also valid to specify the size of the array inside of the square brackets. The number 4 here signifies that the array has a capacity to hold 4 elements. To obtain the length of an array in C++, we can use the sizeOf function. Let's create an int variable named length, which we set equal to sizeOfNums, divided by sizeOfNums at index 0. SizeOfNums will give us the total size of the array in memory, and dividing that by the amount of memory being taken up by one element in the array will give us the number of elements in the array. Then we will output the value of our length variable to the console. When we run the code, notice that 4 was output. This makes sense since our array is storing 4 elements. We can iterate over each element in an array using a for loop. For example, let's create a for loop that starts at int I equals 0, runs while I is less than length, and increments I by 1 each time. Inside of the for loop, we will output nums at index I, and then a new line to the console. When we run the code, notice that each of the elements in our array, values 1 through 4, were output to the console. We can change the value of an array element by referencing its index. For example, let's change the element at index 0 to be 10. When we run the code, notice that 10 is the first element output to the console. In this video, we will go over the answer and explanation of the coding exercise that we just completed. The question asks us to create an array of strings storing the values A, B, and C, and then output its size to the console. Let's create an array of strings named strings, which we assign a size of 3. We will initialize this array with the string values A, B, and C. Then we will output the result of size of strings divided by size of strings at index 0. When we run the code to check our solution, notice that it is correct. In this video, we will learn about vectors in C++. A vector is essentially a resizable array. The array data structure that we learned about is great if you know the exact amount of elements that you need to store. However, once you create an array, you cannot change its size later on in the program. With vectors, you can dynamically add and remove elements as needed. The first step to working with vectors in our C++ program is to include the vector header file at the top of the code. We will also include the string header file. Then, inside of the main function, we will create a vector which stores elements that are strings, which we name v1. To add elements to a vector, we can use the pushback function. Let's add the string abc to v1 using the pushback function. Then we will add the string def to our vector. After that, we will add the string ghi to our vector. Let's check the contents of our vector. We will use a for loop that starts at int I equals 0, runs while I is less than v1.size, and increments I by 1 each time. Inside of the for loop, we will output each of the elements in our v1 vector to the console, separated by a space. When we run the code, notice that the elements ABC, DEF, and GHI were output to the console. To remove the last element from the vector, we can use the popback function. Let's call popback on our v1 vector. Now, when we run the code, notice that only 2 elements were output to the console, ABC and DEF, since GHI was removed when we called the popback function on our vector. The clear function is used to remove all of the elements from a vector. Let's call the clear function on our v1 vector. Then we will output the size of v1 to the console. When we run the code, notice that 0 was output, meaning that the clear function successfully removed all of the elements from our v1 vector. In this video, we will go over the answer and explanation of the coding exercise that we just did. The question asks us to create a vector of integers and add the values 1, 2, and 3 to it. Then we have to output its size to the console. First, let's create a vector of ints named integers. Next, we will use the pushback function to add the integer values 1, 2, and 3 to the vector respectively. Finally, we will output integers.size to the console. When we run the code to check our solution, notice that it is correct. In this video, we will recap the key takeaways from this section of the course. This section covered input, conditional statements, and loops. First, we learned about obtaining user input using cin and the extraction operator. Next, we learned about if, else statements, programming constructs that can be used to write branching code logic in C++. Then came a look at another type of conditional statement, switch statements. A switch statement checks if a condition matches one of the case statements inside of it, and if so, executes the code associated with that switch statement. After that, we learned about for loops, which we can use to execute code over and over a certain number of times. For loops are ideal when we know the amount of iterations we need in advance. Next, we learned about while loops and do-while loops. These programming constructs come in handy when we don't know the amount of iterations we need beforehand, or when we want to execute the loop while a Boolean condition is true. We need to ensure that each loop eventually hits a condition that terminates it, or else we will run into an infinite loop, an error situation where a loop continues running indefinitely and crashes our program. Then we learned about goto statements, which allow us to jump to different labeled sections of the code. Again, please be careful when using goto statements, as doing so can make the code harder to follow. After that, we learned about pointers. Then we learned about arrays and vectors. Arrays have a fixed size, and their size cannot be changed. Vectors are resizable arrays. In this video, we will go over the answers and explanations to the quiz questions for this section. The first question asks us which type of loop we should use when we know the number of iterations that we need. The answer here is for loop. Remember, you should use a for loop when you know the number of iterations that you need. A while loop is used when we don't know the number of needed iterations. The second question asks us what the code will output. We are given an int variable named x assigned a value of 5. Then comes a switch statement checking the value of x. The first case checks if x is 1. Since it isn't, we move to the next case. X is not 2, so the default statement gets hit. Banana is output to the console, and then the break keyword is hit, exiting the switch statement. So the correct answer here is banana. In this video, we will learn about creating user-defined types in C++ code. First, we will learn about structures, aka structs. Then we will learn about classes. After that, we will learn about enumerations, aka enums. Then we will learn about the difference between declaring and defining variables. Next, we will learn about separate compilation. After that, we will learn about namespaces. Then we will recap the key takeaways from this section of the course. Next will come the quiz for this section of the course, and then a video going over the answer and explanation to each of the quiz questions. By the end of this section, you will have an understanding of the various user-defined types that C++ gives us access to. In this video, we will learn about structures, aka structs, in C++. A struct is a data structure that we can use to group several variables that are related. Let's look at an example. At the top of the code, we will include the string header file. To create a struct, we begin by using the struct keyword. Then we provide a name for our struct. Let's name it phone. After that comes a pair of opening and closing curly braces. Inside of here we can add some variables. Let's add a string variable named OS, a float variable named price, and an int variable named memory. There are a couple of key points to note here. Each variable inside of a struct is called a member. So in this case, OS, price, and memory are members of our phone structure. Notice that unlike the array and vector data structures that we learned about in the last section, which can only store one type of variable, a struct can have members of different types. Now we have defined a structure named phone. The next step is to actually create a phone. Let's create a variable of type phone and name it Google Pixel. We can specify the values for the different properties of a phone. Let's assign our Google Pixel an OS of Android. To do this, we type Google Pixel, then a dot, and then the name of the member variable, OS in this case. We will also assign our Google Pixel a price of 100.00F and a memory of 16. Now our Google Pixel is recognized as an Android phone with a price of $100 and a memory of 16 gigabytes. To prove this, let's print out the different properties of our phone. We will first output the string Google Pixel, and then a new line. After that, we will output the OS, price, and memory of the Google Pixel respectively, each prefixed with 2 spaces and ended with a new line character. Then we will output another new line character at the end. When we run the code, notice that the properties of our Google Pixel were output to the console. Let's create another phone. This time we will create a variable of type phone named iPhone 6s. We will assign it an OS of iOS, a price of 50.00F, and a memory of 8. Similar to how we did for the Google Pixel variable, let's output the values of the iPhone 6s's OS, price, and memory to the console. When we run the code, notice that the iPhone has an OS of iOS, a price of 50, and a memory of 8 gigabytes. In this video, we will learn about classes in C++. As you may have learned when programming in other languages, any programming language that has the concept of classes and objects is called an object-oriented programming language. A class is one of the user-defined types that we will learn about in this section. At the top of the code, we will include the string header file. To create a class, we start out by using the class keyword. Then comes the name of the class. For this example, we will create a class named person. Inside of the curly braces comes the variables for our class. We also refer to them as attributes. Our person class will have a public string attribute name and a public int attribute age. Public means that the other code in our program, outside of our class, can access and set these attributes. Now we have a person class with two attributes, name and age. We still need to actually create an object out of the class. An object is essentially an instance of the class, and classes serve as the blueprint for objects. Let's create a variable of type person named person1. We will assign it a name of Rob and an age of 27. Let's output the attributes of person1 to the console so that we can see that the object was correctly created and the values of its attributes correctly assigned. We will output the string person1 and then a new line, then the string name, the name of person1 and then a new line, and then the string age, person1's age, and then a new line. After that, we will output another new line to the console. When we run the code, notice that the attributes of person1 were successfully output to the console. Let's look at another example of creating a person object. We will create a variable of type person named person2. Next, we will assign person2 a name of Sally and an age of 25. Let's output the attributes of person2 to the console. When we run the code, notice that person2 has a name of Sally and an age of 25, just like we specified. In this video, we will learn about enumerations, also called enums. An enum is a type that is defined by the programmer. To create an enum, we can use the enum keyword. We will create an enum named season that we give 4 possible values: winter, spring, summer, and fall. Next, let's create a variable of type season named time of year. We can set time of year equal to summer. Then let's output time of year to the console. When we run the code, notice that 2 was output. This may seem surprising at first, however, remember that enum stands for enumeration. Each enum value that we create gets mapped to an integer value under the hood of the program. By default, it starts at 0, so for this example, winter corresponds to a value of 0, spring corresponds to a value of 1, summer corresponds to a value of 2, and fall corresponds to a value of 3. In the last section, we learned about conditional statements like if and switch. We can combine this concept with enums. For example, let's use an if statement that checks if time of year is equal to summer. If so, we will output time of year to the console. When we run the code, notice that it is summer was output since the value of time of year is summer from our season enum. If we want to change the integers that the enum values are mapped to, we can do so when creating the enum. For example, we could set winter equal to a value of 2, spring equal to a value of 4, summer equal to a value of 6, and fall equal to a value of 8. Let's look at another example of working with enums. We can create an enum named day that has the possible values Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. We will create a variable of type day named weekday. Let's assign weekday a value of Friday. After that, we will utilize a switch statement that checks the value of weekday. In the case that weekday is Monday, we will output Monday to the console and then break from the switch statement. If it is Tuesday, we will output Tuesday to the console and then break from the switch statement. In the event that it is Wednesday, we will output Wednesday to the console and then break from the switch statement. If it is Thursday, we will output Thursday and then break. If it is Friday, we will output Friday to the console and then break out of the switch statement. In the case that weekday is Saturday, we will output Saturday to the console and then use the break keyword. If it is Sunday, we will output Sunday to the console and then break from the switch statement. When we run the code, notice that Friday was output to the console since weekday is holding a value of Friday. In this video, we will learn about 2 important concepts in C++ programming: declaring and defining. These concepts apply to programming constructs like variables and functions. Let's look at how we would declare a variable using C++ code. A variable declaration consists of the type and name of the variable. For example, we could declare an int variable named number. Notice that a variable declaration does not set the value of the variable. It just tells the compiler the type and name of the variable respectively. Defining the variable means assigning a value to it. For example, we can set number equal to 0. Note that it is also valid to both declare and define the variable in one line of code, so we can create an int variable named number and assign it a value of 0, all in one step. As I mentioned at the start of this video, the concepts of declaring and defining apply to more than just variables. They also apply to other programming constructs like functions. When we declare a function, we specify the return type, function name, and parameters for the function. For example, we can create a function named add that has an integer return type and takes in two parameters, an int named num1 and an int named num2 respectively. Defining a function is when we specify the body of that function. For example, inside of our add function we will return num1 plus num2. To run the code inside of a function, we need to do something known as calling the function. For example, inside of C++'s main function we will output the result of a function call to the add function, with 1 and 2 passed into the console. When we run the code, notice that 3 was output to the console, since 1 plus 2 is 3. In this video, we will learn about separate compilation in C++. Separate compilation is a feature of C++. That means the code sees only the declarations of the types and functions used from other files. The definitions of the types and functions are in separate source files and get compiled separately. There are many reasons that separate compilation is a good idea, namely code organization, minimum compilation times, and minimizing the chance of errors. Large projects have a lot of source code, and many projects have not just one, but many developers. There is a need to keep compilation times low while also enabling the sharing of functionality between different files. The declarations of the shared functionality get placed in a file, called a header file, and other files import that header file in order to access its functions. In this way, a header file acts as an interface. For example, when we include a header file like iostream into our program with the include preprocessor directive, that allows the C++ file to utilize any of the functions declared in the iostream header file. So you may have many files like example.cpp, example2.cpp, and example3.cpp, all of which utilize the code in the iostream header file. Separate compilation is what makes this abstraction of functionality possible. If it were not available in C++, then we would have duplicate code, as any reused functionality would be rewritten in each of the CPP files. Instead, we can import the header file at the top of the code, and then use any of its functions in our example1, example2, and example3 programs. In this video, we will learn about namespaces in C++. If you've worked with other programming languages like C#, you may be familiar with the concept of a namespace. Put simply, namespaces are a way to group code together. They help us avoid naming conflicts that could arise when working with large code bases. One common namespace that we've already worked with in this course is std, the standard namespace. Recall that we can import the standard namespace at the top of the code by typing using namespace std. Then we have access to the code from the standard namespace, such as cout. To create a namespace, we can use the namespace keyword. We type the word namespace, then the name of the namespace, example in this case, and then a pair of curly braces surrounding the code inside of the namespace. In this video, we will recap the key takeaways from this section of the course. First, we learned about structures, aka structs. Each variable inside of a struct is called a member. Also, structs can have members of different types, unlike other data structures we learned about, like arrays and vectors. Then we learned about classes. Classes are the cornerstone feature of any object-oriented programming language. We refer to the variables inside of a class as attributes. When we instantiate a class, we call the instantiation of the class an object. Next, we learned about enumerations, aka enums. An enum is a type defined by the programmer, and each possible value of the enum gets mapped to an integer value, which starts at 0 by default. After that, we learned about the difference between declaring and defining variables and functions. Declaring a variable is when we specify the type and name of the variable. Defining it means assigning it a value. Then we learned about separate compilation. Separate compilation is a concept that means C++ code sees only the declarations of the types and functions used from other files, and that their definitions are stored in the source files that get compiled separately. Finally, we learned about namespaces. A namespace allows us to group code together, and we can create a namespace using the namespace keyword. Furthermore, we can import a namespace with the using keyword. In this video, we will go over the answers and explanations to the quiz questions. The first question gives us the code string name and asks us what this code is an example of. The answer is declaring a variable called name. Remember that declaring a variable is when we specify the type and name for it. Defining a variable is when we assign it a value. The second question asks us what standard is in C++. The answer is namespace. Standard is a namespace that contains things like the standard input stream, cin, and the standard output stream, cout. In this section of the course, we will learn about intermediate level topics in C++ programming. First, we will learn about libraries. Then we will learn about the standard library. Next, we will learn about file I/O. Then we will learn about working with dates and times using C++ code. After that, we will learn about recursion. Next, we will learn about regular expressions, aka regex. After that, we will learn about linked lists and their implementations in C++. Next, we will learn about trees in C++. Then we will recap the key takeaways from this section of the course. Next will come the quiz for this section, and then a video explaining the answers to the quiz. By the end of this section, you will have a working knowledge of intermediate level C++ coding. In this video, we will learn about libraries and the role that they play in C++ programming. A library is a collection of pre-written code that we use to make repeated system calls. Libraries take care of the details of what each function does. We call their functions. In this way, the library functions as an interface. Not only can we create our own custom libraries, but most compiled languages have a standard library. C++ has a standard library, and we will learn about it in the next lecture. In this video, we will learn about C++'s standard library. The standard library is made up of two parts, which are the standard function library and the object-oriented class library, respectively. It is essentially a collection of useful classes and functions. To learn more about the standard library and take a look at its contents, we can navigate to the following URL, docs.microsoft.com/en-us/cpp/standard-library/cpp-standard-library-overview. By familiarizing yourself with the standard library and the functionality that it offers, you can help ensure that you don't reinvent the wheel and save time and effort when programming. In this video, we will learn about using C++ for file input and output, also called file I/O. Up at the top of the code, we need to include the fstream header file, which gives us access to code to work with files. Let's create a file that we will write some text to. To do this, we will create a variable of type ofstream, named example1, that we name example1.txt. ofstream is a class that we use in order to write to files. Next, we will actually write some text to the file. First comes the name of the variable, example1. Then we put the insertion operator. Finally comes the text we want to write to the file as a string, which in this case will be the contents for the file. After writing to the file, we need to close it, so we can type example1.close, which calls the close function to close our file. Let's run the code. To check if the file was created with the contents that we specified, we can right-click on the tab of the CPP file in Visual Studio Code and select Reveal in Finder. This will open up the folder where our CPP file is stored. In that same folder will be a file named example1.txt, and if we double-click on this file, notice that the contents we wrote to it are present inside of it. Now that we know how to create and write to a file, let's learn how to read text from a file. We will start out by creating a variable of type ifstream named example2, and pass the string example1.txt into the constructor, so that the contents of the file get added to our example2.txt file. Then we will have a character variable named c that we set equal to example2.get. While example2.good, we will output c to the console. Then we will set c equal to example2.get. The good function lets us know that we haven't reached the end of the file, and that there are more characters to process. The get function will grab the next character to process in the file. When we run the code, notice that the contents of the file were printed to the console. In this video, we will learn about working with dates and times in C++. The first step to doing so is to import the ctime header file into our program using an include statement. To start out, we will create a variable of time t, named now, that we set equal to a time object with a value of 0 passed in. Time will return the current time, represented as the number of seconds that have passed since January 1st, 1970. This is a special date called the Unix epoch, which gives us a uniform date to use as the basis for working with UTC, which stands for Universal Time Coordinated. Another important feature of working with dates and times in C++ is the tm struct. It is responsible for holding date and time information. For example, let's create a pointer of type tm named nowLocalTime that we set equal to local time with ampersand now passed in. Before we move forward, I want to take the time to go over the different date and time information that the TM struct gives us access to, because it is important to understand the tools that the language gives you access to when programming. This table shows the information that we have access to. TM sec will give us the seconds, TM min will give us the minutes, TM hour will give us the hour, TM mday will give us an integer value between 1 and 31, representing the day of the month. TM mon will give us an integer between 0 and 11, representing the month. TM year gives us the year since 1990. TMW day gives us the days since Sunday. TMY day gives us the days since January 1st. And TM ISDST gives us the hours of daylight savings time. Now that we know more about the TM struct, let's take a look at how we can work with it in C++. Next, we will output the year to the console. To do this, we print the result of 1900 plus the value of the TM year field. When we run the code, notice that the year was output to the console. Let's look at an example that is a bit more complex and combines using several of the TM struct's fields. Let's create an integer variable named month that we set equal to 1 plus now local times TM month value. Next, we will create an int variable named day that we set equal to the TM mday value. Then we will create an int variable year that we set equal to 1900 plus TM year. After that, we will create an int variable named hour that we set to 5 plus TM hour. Next, we will create an integer variable minutes set equal to 30 plus TM min. Then we will have an int variable named seconds that we set to TM sec. The code we just wrote gives us a variable holding the current month, day, year, hour, minutes, and second. Let's output month, then a slash, then day, then a slash, then year, then a space, then hour, then a colon, then minutes, then a colon, then seconds, and finally a new line to the console. When we run the code, notice that the date information and time information for the current date and time are output to the console. In this video, we will go over the answer and explanation of the coding exercise. The problem asks us to output the current year to the console. When we want to work with dates and times in C++, the first step is to include ctime, as we learned earlier in this section, as it gives us access to important date and time classes. Let's create a variable of type timet, named now that we set equal to time with 0 passed in. Then we will create a pointer of type tm that we name now local time, which we set to local time with ampersand now passed in. Next, we will create an int variable named year that we set equal to 1900 plus the TM year value of now local time. And finally, we will output year to the console. When we run the code to check our solution, notice that it works, meaning we correctly solved the problem. In this video, we will learn about recursion. Put simply, recursion is when a function calls itself. Up until this point in the course, we've learned how to solve problems iteratively, using iteration with for loops and while loops. In order for a function to be recursive, it needs to have the following properties. The function needs to call itself, it needs to have at least one base case, and each call to the function needs to progress closer to the base case. I mentioned an important term in the second and third points, base case. A base case is a condition that causes the function to terminate. In other words, to stop calling itself. Without a base case, the code will execute indefinitely. Each recursive call gets stored on the call stack, and since the call stack has a finite amount of memory, it eventually runs out and will throw a Stack Overflow exception. Fun fact, this is what the programming help website Stack Overflow is named after. Let's look at some examples of working with recursion using C++ hands-on. We'll start out with a basic example and work up through more advanced code. To start off, let's use recursion to create a program that gives us the factorial for a number. For those unfamiliar with the term, a factorial is when we multiply a number by all the numbers less than it. For example, 3 factorial is 3 times 2 times 1, which makes 6. 4 factorial is 4 times 3 times 2 times 1, or 24, so on and so forth. Let's create a function that returns an integer, which we will name factorial. Our factorial function will take in one parameter of type int, named num. Inside of this function, we will check if num is greater than 0. If so, we will return num times the result of a call to the factorial function, with num minus 1 passed in. Else, we will return 1. That wraps up our factorial function. The next step is to go inside of C++'s main function. We will output the result of a call to our factorial function with 4 passed into the console. When we run the code, notice that 24 was output, which is the correct answer for 4 factorial. If we change the number passed into the factorial function to 3, notice that 6 is output, which is the correct result for 3 factorial. The next example of recursion we will look at is slightly more complex, and if you studied computer science in college, you will almost certainly be familiar with it. It is the Fibonacci sequence. The pattern starts with the number 1, and is formed by adding the prior 2 numbers in the sequence to it. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 13 plus 8 is 21, so on and so forth. How would you code this algorithm recursively using C++ code? We'll start out by creating a function that returns an int named fib, which takes in one parameter of type int named n. Inside of this function, we will use an if statement to check if n equals 0 or n equals 1. If so, we will return 1. These are our base cases. Else, we will return fib with n minus 1 passed in, plus fib with n minus 2 passed in. Inside of the main function, let's test our code. We can output the result of fib3 to the console. When we run the code, notice that the correct output of 3 was printed. Changing the argument passed into the fib function to 7, and then running the code results in 21 being output. Great, our fib function works properly. Let's look at another popular example of recursion commonly taught in college, the Tower of Hanoi. Before we jump into coding a solution, let's open up a web browser and navigate to mathsisfun.com/games/towerofhanoi.html to see an interactive version of this challenge. Tower of Hanoi is a puzzle that features 3 towers, or pegs. There are discs of various sizes, from smallest on top to largest on the bottom. The objective of this game is to move all of the discs to Tower 3, with the rule that we cannot place a larger disc onto a smaller disc. We want to do this in the least amount of moves possible. For example, given 3 discs, we can move the small disc to Tower 3, then the medium disc to Tower 2, the small disc to Tower 2, the large disc to Tower 3, the small disc to Tower 1, the medium disc to Tower 3, and the small disc to Tower 3, on top of the other 2, to solve the puzzle. Let's create a function with a void return type named Tower of Hanoi. It will take in a parameter of type int named n, a parameter of type char named from, a parameter of type char named to, and a parameter of type char named extra. First, we need a base case. If n equals 0, we will return from the function. After that, we will make a recursive call to the Tower of Hanoi function with n minus 1 passed in as the first argument, from passed in as the second argument, extra passed in as the third argument, and 2 passed in as the fourth argument. Next, we will output move disk, then the number of the disk n, then the word from, then the from disk, then the word to, then the to disk, and then end L, aka the new line. Then we will make another recursive call to the Tower of Hanoi function and pass in n-1 as the first argument, extra as the second argument, 2 as the third argument, and from as the fourth argument. That wraps up the Tower of Hanoi function. The next step is to go inside of C++'s main function and test it. Let's create an int variable named n that we set equal to 3. Then we will call the Tower of Hanoi function with n passed in as the first argument, the character 1 as the second argument, the character 3 as the third argument, and the character 2 as the fourth argument. After that, we will run the code. Notice that the steps to solving the puzzle are printed to the console. Great, our code worked. Let's run another test. This time we will change n from 3 to 4. Then we will run the code, and you'll see the steps correctly printed for when there are 4 disks. Great work. In this video, we will go over the answer and explanation of the coding exercise. The problem states, given an integer n, return true if it is a power of 2. Otherwise, return false. It is also clarified that an integer n is a power of 2 if there exists an integer x, such that n equals 2 to the x. Let's think about how we would go about solving this problem. First, let's start by considering the powers of 2. 2 to the 0th power is 1. 2 to the first power is 2. 2 to the second power, or 2 squared, is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64, and so on. Notice that if you take any of these numbers and keep dividing it by 2, you'll eventually get a value of 1. Therefore, one of our base cases for our is_power_of_2 function will be if n equals 1, we will return true. Next, we need to account for if we divide the number by 2 over and over, and it ends up not being a power of 2. Another way to say this is that when the number is divided by 2, we are left with a remainder. For example, 3 divided by 2 is 1.5. So our second base case will be if n modulus 2 does not equal 0. If that is the case, we will return false. Now that we have defined our base cases, we need to write code that will progress towards them each time the function is called. In this case, we will divide n by 2. Using the divide equals operator allows us to both divide n by 2 and assign the new value to it all in one step. Finally, we need to make a recursive call to the function. Let's return the result of is_power_of_2 with n passed in. When we run the code to test our solution, notice that it is correct. In this video, we will learn what regular expressions are and how to work with them when programming with C++. The acronym regex stands for regular expressions. It is used for pattern matching, commonly for coding find and replace functionality with strings. The first step to working with regular expressions in C++ is to include the regex header file at the top of the program. Let's look at an example of how regex can be used. We will start out by creating a variable of type string, named s, that we assign the string value of Batman. Next, we will create a variable of type regex named pattern. Inside of the constructor, we pass in the string of the pattern we want to check. For example, this is how we would check if the string starts with the word bat, followed by any other characters. To check if a match was found between the string and the pattern, we can use the regex match function. For example, let's use an if statement and check if there is a match by calling the regex match function and passing in x as the first argument and pattern as the second argument. Inside of this if statement, we will output the string match to the console. When we run the code, notice that match was printed to the console since the string Batman does start with the word bat. In this video, we will learn what linked lists are and how to implement a linked list using C++ code. A linked list is made up of nodes. The first node in a linked list is called the head, and each node in the list points to the next. Each node contains some data like a value, as well as a pointer to the next node in the list. A linked list is referred to as a singly linked list if the links to the nodes are in one direction. Sometimes, a linked list has links in both directions, so each node also has a field called previous. We call this type of linked list a doubly linked list. The C++ standard template library has built-in collections for these two types of linked list. The forward list container is a type of singly linked list, and the list container is a doubly linked list. We will learn about each of these in the next section of the course, where we learn about the main container types in C++'s standard template library. The first step to creating a linked list in C++ is to create a node class. This class will have two public attributes, one of type int named value, and one of type node pointer named next. Inside of the main function, we will start out by creating a node pointer named head. Then we will have a node pointer named first that we set to a new node. We will also have a node pointer named second that we set to a new node, followed by a node pointer named third set to a new node. After that, we will set the value of first to 1, second to 2, and third to 3. We will set first's next pointer to second, second's next pointer to third, and third's next pointer to null. Then we will set head equal to first. While head does not equal null, we will output the value of head to the console, followed by an arrow formed by using a dash and a closing angular bracket. After that, we will set head equal to its next value. At the bottom of the function, outside of the while loop, we will output null to the console, since the final value that a linked list points to is null. When we run the code, notice that our linked list is made up of nodes 1, 2, and 3, and that 3 points to null, signifying the end of the linked list. The question wants us to convert a linked list representing a binary number into an integer. Let's create a variable of type string named s that we initialize to a value of an empty string. Then we will have an int variable named result set to a value of 0. While head is not null, we will convert the value of head to a string and concatenate it to s. Then we will set head equal to head's next value. Outside of the while loop, we will create an int variable named power that we assign a value of 0. After that, we will have a for loop that starts at int I equals s.length minus 1, runs while I is greater than or equal to 0, and decrement I by 1 each time. Inside of this for loop, we will add s at index I cast to an integer times 2 to the power of our result variable. Then we will increment the power variable. Outside of the for loop, we will return result. When we run the code to check our solution, notice that it is correct. In this video, we will learn about trees in C++. A tree is a hierarchical data structure. It is made up of nodes. The node at the top is called the root node. Each node can have one or more children. At the bottom of the tree are nodes that don't have any children. We call these nodes leaves. There are many types of trees in computer science, including binary trees, trees where each node has no more than 2 children, binary search trees that have higher values as right children and lower values as left children, and tries, trees with nodes that store letters and branch into different words. Let's learn how to implement a tree using C++ code. First, we will create a node class that has 3 public attributes, an int named value, a node pointer named left, and a node pointer named right. Then we will go inside of the main function. Let's create a node pointer named root that we set equal to a new node object. We'll also create a node pointer named left child, set to a new node, and a node pointer named right child, set to a new node. We will give root a value of 2, left child a value of 1, and right child a value of 3. After that, we will set root's left attribute to left child and root's right attribute to right child. Then we will output the tree to the console. Let's output a few empty spaces and then the value of the root. After that, we will output a new line, then a forward slash, and then 2 backslashes. One of these is needed to escape the other, since backslashes are used as escape characters. Next, we will output a new line, then the value of root's left attribute, then some spaces, and then the value of root's right attribute. When we run the code, notice that a tree diagram is output with a root of 2, a left child of 1, and a right child of 3. In this video, we will go over the answer and explanation to the trees coding exercise. We are given a tree that consists of 3 nodes, a root, a left child, and a right child. The problem asks us to return true if the sum of the values of the 2 children equals the value of the root, and false otherwise. To do this, we will go inside of our checkTree function. Let's return if root's value equals the sum of root's left child value and root's right child value. When we run the code to check our solution, notice that it is correct. In this video, we will recap the key takeaways from this section of the course. A library is a collection of pre-written code that we can use in the C++ programs we write so as not to reinvent the wheel. The C++ standard library is made up of 2 parts, the standard function library and the object-oriented class library. Using C++ code, we can read from and write to files. To write to a file, we use the OFStream class. The IFStream class allows us to read the contents of a file. We can work with date and time data in C++ by including ctime at the top of the code, and then utilizing the time_t class and tm struct. Recursion is when a function calls itself. In order for a function to be a working recursive function, it needs to have at least one base case, and each call to the function needs to progress closer to the base case. Regular expressions, or regex, allow us to perform find and replace functionality on a string using pattern matching. Linked lists are a special type of data structure. In C++, we can implement a linked list by hand, or we can use one of the built-in types, forward list, which is a singly linked list, or list, which is a doubly linked list. Trees are a hierarchical data structure that we can implement. There are many types of trees, including binary trees, binary search trees, and tries. When we visit each of the nodes in a tree, we refer to that as traversing the tree. The main types of traversal you can do are depth first and breadth first. With depth first, you visit a node's children before its neighbors. Breadth first traversal involves visiting each of a node's neighbors before its children. In this video, we will go over the answers and explanations to the quiz questions. The first question asks us what type of exception we get if our recursive function never hits the base case. The answer is a Stack Overflow exception. The second question asks us what the OFStream class is used for. The answer is writing to a file. Remember that the OFStream class is used to write to a file. The IFStream class is used to read from a file. In this section of the course, we will learn about containers in C++. We will learn about vectors, forward lists, lists, decks, sets, maps, stacks, and queues. Then we will recap key takeaways from this section of the course. After that comes the quiz for the concepts taught in this section of the course, and then a video going over the answers and explanations to the quiz. By the end of this section of the course, you will understand how to work with containers in C++ programming. In this video, we will learn about vectors in C++. A vector is a collection similar to an array, but whereas an array is of a fixed size, a vector can increase or decrease in size dynamically. Just like arrays, vectors can only store elements of similar data types, so we can have a vector of integers or a vector of characters, but not a vector that has both integers and characters in it. To begin working with vectors, we need to include the vector header file at the top of the code, which will import it from the C++ standard template library, the STL. Let's look at an example of working with vectors in C++. First, we will create a variable of type vector that stores integer elements, named list. To add an element to a vector, we can use the pushback function. Let's add 2 to our vector of ints by typing list.pushback and passing in 2. After that, we will add the integers 4 and 8 to the list, using the pushback function. We can use a for loop to iterate over each of the items stored in a vector. For example, let's have a for loop that starts at int I equals 0, runs while I is less than list.size, and increments I by 1 each time. Inside of this for loop, we are going to output each of the items in the vector to the console. We can access an element in a vector with its index by using the at function. Let's output list at I, and then a space to the console. When we run the code, notice that each of the elements 2, 4, and 8 was printed out. Let's learn about some more functions that apply to vectors and see how they would work on our vector named list that we've been working with. To retrieve the first element in a vector, we can utilize the front function. We can print out the string first element is, then a call to list.front, and then a new line character to the console. Obtaining the last element in a vector could be achieved using the back function. For example, we will print out last element is, then make a call to list.back, and then a new line character to the console. To check how many elements are currently stored in a vector, we can use the size function. For example, let's output the string size before clear is, then list.size, and then a new line to the console. We can remove all elements from a vector using the clear function. For example, let's type list.clear, which will remove all of the elements 2, 4, and 8 from our list vector. To check that the clear operation worked properly, we will output size after clear is, then the size of the list, and then a new line to the console. Checking if a vector is empty can be done using the empty function. For example, let's output isEmpty, then list.empty, and then a new line to the console. When we run the code, notice that the first element in our vector is 2, the last element in the vector is 8, the size before the clear is 3, the size after the clear is 0, and isEmpty is equal to 1. Recall that 1 stands for a value of true. To remove the last element from a vector, we can use the popback function. After pushing back 2, 4, and 8 onto our vector, let's make a call to list.popback. Then we will print out each of the elements in the vector using a for loop. When we run the code, notice that the vector only contains 2 and 4, meaning 8 was removed from the vector using the popback function. Another way to add elements to a vector is using the following syntax. Say we create a vector of ints named list2 with a set of parentheses right after the variable name and pass in 4 as the first argument and 0 as the second argument. The 4 is the size, meaning our vector will hold 4 elements. The 0 is the value for each of the elements. To check that these elements were added to the list correctly, we will iterate over each item in our list2 vector using a for loop and output them to the console. When we run the code, notice that 4 zeros were output to the console, just like we expected. We can change the value of an element in a vector using its index. For example, we will reference the element at index 0 using the at function and assign it a value of 1. Now, when we run the code, notice that the first element in our list2 vector is 1, and the other 3 values are 0. Another concept relating to vectors is the concept of iterators. An iterator is used to point to the memory address of an element in a vector. An iterator is very similar to the concept of a pointer in C++. For this next example, let's create a vector of characters named list that we assign the character values A, B, C, and D to. Next, we will create a vector iterator by typing vector char, and then 2 colons, then iterator, and then the name of the iterator, which will be I. After that, we will set I to list.begin. The begin function returns an iterator that points to the first element in a vector. To see this, let's output the value that I is pointing to the console. When we run the code, notice that the element at index 0 in our list vector is A. We can also use iterators and for loops. For this next example, let's create a vector of integers named numbers that contains the integer values 1, 2, 3, 4, and 5. For iterator it equals numbers.begin, while it does not equal numbers.end, and incrementing I by 1 each iteration, we will output the value of the element it is pointing to the console. When we run the code, notice that 1, 2, 3, 4, and 5 were output to the console. In this video, we will go over the answer and explanation to the coding exercise. The question gives us a declaration, a vector of ints named integers, and instructs us to add the elements 1, 2, and 3 to it. That is part 1 of the question. The second part asks us to output each of the elements to the console, with a space between each. Recall that we can use the pushback function to add elements to our vector. Let's call the pushback function to add the elements 1, 2, and 3 to our vector. Then we will iterate over each element in the vector and output it to the console using the at function. Don't forget to output a space after the number so that each of the numbers is separated by a space, as specified in the question. In this video, we will learn about forward lists in C++. A forward list is a singly linked list class that is provided by the standard template library. To begin working with forward lists, we will include the forward list header file at the top of the program. We will start by declaring a forward list of integers named example. To add values to the front of our forward list, we can use the pushFront function. Let's add the values 5, 4, 3, 2, and 1 to example. To obtain the front element in our forward list, we can make a call to the front method. Let's output the string front element is, and then example.front. When we run the code, notice that 1 is the front element of our forward list. Next, let's call the pushFront function and pass in 0. If we output the value of the new front element to the console and run the code, notice that 0 is output. We can use a for loop to iterate over each element in the forward list. We will output the element and then an empty space to the console. When we run the code, notice that the values 0 through 5 were printed out. To reverse a forward list, we can use the reverse function. Let's reverse our forward list and then output the values to the console. When we run the code, notice that the forward list was output in reverse order. In this video, we will go over the answer and explanation to the forward lists coding exercise. The question prompts us to create a forward list that has the string values A, B, and C in that order. The first step is to include the string header file at the top of the program. Then we will declare a forward list of strings named example. After that, we will use the assign method to add the values A, B, and C to it. Then we will return example. When we run the code to check our solution, notice that it is correct. In this video, we will learn about lists in C++. Lists, like vectors, are available in the standard template library. If you're familiar with how a linked list works, a list in C++ is essentially a doubly linked list. Unlike vectors, a list does not store its elements in contiguous blocks of memory. Therefore, it is slow to traverse a list, but insertion and deletion are fast. The first step to working with lists in C++ is to include the list header file at the top of the program. Let's create a list of integers named integers. To add an element to the front of a list, we can use the pushFront function. For example, let's call the pushFront function on our integers list to add 1 to the front of it. To add an element to the back of a list, we can utilize the pushBack function. Let's call pushBack on our integers list and pass in a value of 2 to add 2 to the end of our list. The front function lets us retrieve the front element in a list. For example, let's output front element is and then the value of integers.front. When we run the code, notice that 1 was output. This makes sense since 1 is the first element in our list. In a similar fashion, the back function allows us to obtain the value of the last element in the list. For example, let's output the string back element is and then the result of a call to integers.back to the console. When we run the code, notice that 2 is output to the console, which makes sense since 2 is the element at the back of our integers list. Let's add a few more elements to the back of our list. We will call the pushBack function to add 3 and 4 to our list respectively. Then we will output integers.back to the console. When we run the code, notice that 4 was output, since 4 is now the last element in our integers list. The popBack function will remove the last element of the list. After we add 4 to the list and before printing the back value to the console, let's type integers.popback. Now, when we run the code, notice that 3 is the last element in the list. This is because 4 was removed when we called the popback function on our integers list. For the next example, let's assign our integers list the values 10, 0, 7, 3, and 4. We can sort a list using the sort function. Let's type integers.sort. Then we will create a list iterator named it. To see the order of the elements in the list, let's use a for loop that starts at it equals integers.begin, runs while it does not equal integers.end, and increments it by 1 each time. Inside of this for loop, we will output a new line, and then the value that the iterator is pointing to the console. When we run the code, notice that the values in the list are sorted in ascending order, thanks to the call to the sort function we made. To reverse a list, we can call the reverse function. For example, after we make a call to the sort function, let's add a call to the reverse function. When we run the code, notice that the elements were output in descending order, since we reversed the list with a call to the reverse function. For the next example, let's assign our iterator to integers.begin, so that it is pointing to the first element in our integers list. To insert a value into the list, we can use the insert function. For example, let's make a call to the insert function and pass in iterator it as the first argument, and 1 as the second argument. When we run the code, notice that 1 is the first element in the list since we inserted it into the list. The assign function allows us to replace the current elements in the list with the new elements that we specify. For example, after we create the integers list, let's make a call to integers.assign. The first argument we pass in is the count, and the second argument is the value. For example, passing in 5 as the first argument and 3 as the second argument means that we are replacing the contents of our list with 5 3s. Let's use the pushBack function to add 4 to the end of the list. Then we will call the remove function and pass in 3. Remove will delete all occurrences of the specified element in the list. So passing 3 in like we did here means that all of the 3's in the list will be removed. When we run the code, notice that 4 is the only element in the list. We can also remove all the elements that fit a specified condition. For this next example, we will go above the main function and create a function that returns a bool named even, that takes in a constant value named value. Inside of this function, we will return the result of value modulus 2 equals 0. Since the modulus operator gives us the remainder of a division, if there is no remainder when the value is divided by 2, it means that the number is even. If there is a remainder, the number is odd. Inside of our main function, let's create a list of ints named integers that we will fill with the values 1 through 6. Next, we will use the removeIf function to remove all of the even elements from the list. When we run the code, notice that our list only contains the odd elements 1, 3, and 5, since all of the even elements were removed. We can use the erase function to delete a specified element from the list. For example, after creating the iterator it, let's call integers.erase and pass in it. Since our iterator is pointing at the first element in the list, this is the element that will be removed. Notice when we run the code that the elements 3 and 5 were output to the console, but 1 was not, since the erase function removed it from the list. To remove all elements from a list, we can use the clear function. For example, let's call the clear function on our integers list. Then we will output isEmpty and the result of a call to integers.empty. The empty function will return 1 if the list is empty, and 0 if it isn't. When we run the code, notice that the list is empty, thanks to the clear function we called above. In this video, we will go over the answer and explanation to the coding exercise. We are given a list of integers 10, 0, 5, and 2, and asked to sort the list in descending order from highest to lowest. One way to do this is to call the sort function to sort the elements in the list. Now the list is sorted from lowest to highest. To order the elements in the list in descending order, we can call the reverse function on the integers list. Finally, we will return our integers list. In this video, we will learn about decks in C++. Like the other containers we learned about, they are a part of C++'s STL, Standard Template Library. For those of you familiar with the regular queue data structure in programming, a queue functions as a line at a store, first in, first out. The first person that gets online is the first person helped by the cashier. New people that get on the line go to the back of the line, so insertion is done at the end of a queue. A deck is a double-ended queue. With decks, both insertion and deletion of elements can be done at either end, the front or the back. To begin working with decks in C++, we need to include the deck header file at the top of the program. Let's start out by creating a deck of integers named example. We can add an element to the back of the deck using the pushback function. For example, let's use the pushback function and pass in a value of 5 to add 5 at the rear of our deck. The pushFront function can be used to add an element to the front of the deck. For example, let's push the elements 10 and 100 onto the front of the deck using the pushFront function. To iterate through the items in our deck, we can create an iterator. Let's create an iterator to iterate over a deck of ints named it. Then we will have a for loop that starts at it equals example.begin, runs while it is not equal to example.end, and increments it by 1 each iteration. Inside of the for loop, we will print out the value in the deck that it is pointing to for that iteration, and then a new line. When we run the code, notice that the elements 100, 10, and 5 were output to the console. This ordering makes sense since we pushed 5 to the back of the deck, then pushed 10 onto the front of the deck, and then 100 onto the front. Let's look at some of the other functions we can use when working with decks. The size function allows us to check how many elements our deck is currently storing. For example, we can output the size of the deck to the console. Using the front function, we'll return the element at the front of the deck. In a similar fashion, the back function will return the element at the rear of the deck. We can also use the at function to retrieve the element at a particular index. For example, passing in an index of 1 will retrieve the second element in our deck. When we run the code, notice that the size is 3, the front element is 100, the back element is 5, and the element at index 1, the second element in the deck, since indexing starts at 0, is 10. In this video, we will go over the answer and explanation to the coding exercise. We are asked to add the character D to the end of this deck using a function call. Recall that we can add an element to the back of a deck using the pushback function. Let's call the pushback function and pass in D. When we run the code to check our solution, notice that it is correct. In this video, we will learn about sets in C++. Sets are another type of container in the C++ standard template library. A set is great for when we want to work with sorted, unique data. Items in a set will always be sorted regardless of the order that they are added to the set in. Also, a set cannot contain duplicates, so if we try to add a duplicate element to a set, it will not get added, and only one of that element will remain in the set. To begin working with sets in C++, we need to include the set header file at the top of our code. Let's create a set of ints named integers. Next, we are going to add some elements to the set. To add elements to a set, we can use the insert function. Let's insert the values 20, 30, 15, and 0 to our integers set. Then we will use a for loop to iterate over each integer I in our integers set. Inside of the for loop, we will output I to the console, and then a new line. When we run the code, notice that the elements in our set were output to the console. If we want to order the numbers in a set in descending order, we can use the following syntax when declaring our integers set. We put a comma after int, and then we will add the word greater with int inside of angular brackets. It is important to note here that there needs to be a space between the two closing angular brackets, or you will get a compile time error. When we run the code, notice that the elements in the set were output in descending order. Sets cannot contain duplicates. For example, if we try to insert another 30 into the set, and then run the code, notice that the set only contains one instance of the element 30. This is because sets will not allow duplicates. The find function will give us an iterator to the element in the set if it finds it, else it will return a pointer to one past the last element in the set, the end pointer. First, let's create an iterator for a set of integers named it, that we set to a call to integers.find and pass in 20. Then we will have a for loop starting at it, running while it is not equal to integers.end, and incrementing it by 1 each time. Inside of the for loop, we will output asterisk it, and then a new line to the console. When we run the code, notice that 20, 15, and 0 were output. In this video, we will go over the answer and explanation of the coding exercise. We are given a set of integers named numbers, storing the values 10, 20, 30, and 40. The question asks us to log each element from element 20 to the end of the set to the console, using a for loop, and output a new line after each number. To start, let's create an iterator for a set of integers, named it, that we set equal to numbers.find and pass in 20. Then we will have a for loop that starts out at our iterator it, runs while it is not equal to numbers.end, and it increments it by 1. Inside of this for loop, we will output the value that it is pointing to the console, followed by a new line. When we run the code to check our solution, notice that it is correct. In this video, we will learn about maps in C++. Maps are containers that store elements associatively in key-value pairs. If you've worked with languages like C# or Python, a map is very similar to a dictionary in those languages. The first step to working with maps using C++ code is to include the map header file at the top of the code. Let's create a map that stores keys as strings and values as integers, named example. To insert key-value pairs into a map, we can use the insert function. Let's call the insert function to insert a pair with a key of the string 1 and the integer value 1 to our map. Then we will insert another pair with the key of the string 2 and an int value of 2, and another key value pair with a key of the string 3 and the int value 3. Let's learn another way to add key value pairs to a map in C++. First, we will create another map of strings to ints named example2. Then we will type example2, then square brackets, the string value 1, and set it equal to the int 1. This is how we would add the key with a string value of 1 mapped to an int value of 1. Next, we will add the key value pair 2, 2 to the map, and then 3, 3 to the map. We can access a value by referencing the key inside of square brackets. For example, we can output the value that corresponds to the string 1 in our example2 map. When we run the code, notice that the integer value 1 was output to the console. To remove all of the key value pairs from a map, we can use the clear function. For example, let's call the clear function on our example2 map. Then we will output if the map is empty by utilizing the empty function. When we run the code, notice that the empty function returned a value of 1, meaning true. In this video, we will go over the answer and explanation to the coding exercise. We are given a map declared with keys and values as strings, and instructed to add 3 key value pairs to it. One having a key of secret 1 and a value of ABC, another having a key named secret 2 and a value of DEF, and a third with a key of secret 3 and a value of GHI. To add elements to a map, recall that we can use the insert function. Let's insert a pair of strings with a key of secret 1 and a value of ABC. Then we will insert a pair of strings with a key of secret 2 and a value of DEF. Finally, we will insert a pair of strings with a key of secret 3 and a value of GHI. Don't forget to return the map at the bottom of the function. When we run the code to check our solution, notice that it is correct. In this video, we will learn about stacks in C++. Stacks are a container type provided by the STL. A stack follows the principle of LIFO, last in, first out. The last element added to the stack is at the top of the stack. To begin working with stacks, we can include the stack header file at the top of the code. Inside of C++'s main function, we will declare a stack of integers named s. To add elements to a stack, we can use the push function. For example, let's push the values 1, 2, and 3 onto the stack using the push method. The top method allows us to look at the top value on the stack. We will output the string top and then the value of s.top to the console. To remove the top element from the stack, we can use the pop function. Let's call s.pop and then output the top value to the console. To obtain the size of the stack, we can use the size method. Let's output the size of the stack to the console. In this video, we will go over the answer and explanation to the stacks coding exercise. The first thing we will do is include the stack header file at the top of the code. Let's create a stack of characters named opening. Then we will have an int variable named max that we initialize to a value of 0, and an int variable named count initialized to a value of 0. For int I equals 0, while I is less than s.length, incrementing I by 1 each iteration, we will check if s at index I equals an opening parenthesis. If it does, we will push s at index I onto the stack. Then we will increment count. If count is greater than max, we will set max equal to count. Else, if s at index I is equal to a closing parenthesis, we will pop the top element from the opening stack. Then we will decrement count. At the bottom of the function, we will return max. When we run the code to check the solution, notice that it is correct. In this video, we will learn about working with queues in C++. Queues follow the principle of FIFO, first in, first out, meaning the first element added to the queue gets added to the front of the queue, and the subsequent elements you add get added to the end. Think of a queue as a line at a store. The customers are helped in the order they got on the line. To begin working with queues, the first step is to include the queue header file at the top of the code. Inside of C++'s main function, we will declare a queue of integers named queue. To add elements to the queue, we can use the push function. Let's push the elements 1, 2, and 3 onto the queue. Let's output the front element of the queue to the console. To retrieve the front element of the queue, we can use the front function. When we run the code, notice that 1 was printed to the console, since it was the first element added to the queue, and queues follow the principle of FIFO, first in, first out. Next, let's output the back element to the console using the back function. When we run the code, notice that 3 was output to the console. After that, let's output the size of the queue to the console. To do this, we can use the size function. When we run the code, notice that 3 was output to the console, which makes sense since our queue contains the elements 1, 2, and 3. To remove the front element from the queue, we can use the pop function. Let's call queue.pop. Then we will output the front element of the queue to the console. When we run the code, notice that 2 was output since 1 was removed when we called the pop function. Let's output the size of the queue to the console using the size function. When we run the code, notice that 2 was output to the console, which makes sense since the queue contains the elements 2 and 3. In this video, we will go over the answered explanation to the queues coding exercise. The question asks us to create a queue of strings named example and add the strings A, B, C, and D to it. Inside of the main function, we will declare a queue of strings named example. Then we will use the push function and push the strings A, B, C, and D onto the queue. At the bottom of the function, we will return example. When we run the code to check it, notice that our solution is correct. In this video, we will recap the key takeaways from the material covered in this section of the course. This section covered the main container structures in C++'s standard template library, or STL, vectors, lists, decks, sets, and maps. Vectors are dynamically sized containers that store elements of the same data type in a contiguous block of memory. Forward lists are singly linked lists. Lists are doubly linked lists that do not store elements in contiguous memory. Insertion and deletion are fast, but traversal is slow. Decks are double-ended queues where both insertion and deletion can be done at either end, the front or the back. Sets store elements in order and cannot contain duplicates. Maps store key-value pairs that are stored in order according to the key values. Stacks follow the principle of LIFO, last in, first out. Queues follow the principle of FIFO, first in, first out. In this video, we will go over the answers and explanations to the quiz questions. The first question asks if we don't know how many elements a container will need to hold, we should use. Our choices are array and vector. The correct answer is vector. Recall that vectors essentially function as resizable arrays. Arrays in C++, on the other hand, have a fixed size. The second question asks us what the empty function does when it is used on a collection. The correct answer is that it returns 1 if the collection is empty, and 0 otherwise. The third question asks us which data structure follows the principle of LIFO. Last in, first out. The answer here is stacks. Recall that queues, on the other hand, follow the principle of FIFO, first in, first out. In this section, we will learn about object-oriented programming, also known as OOP, using the C++ programming language. First, we will learn what object-oriented programming is. Next, we will learn about the 4 pillars of OOP, which are inheritance, abstraction, encapsulation, and polymorphism. After that, we will learn about working with classes in C++. Then we will learn about objects in C++. Next, we will learn about inheritance and how to work with it in C++. Then we will recap the key takeaways from this section of the course. After that will come the quiz for this section of the course, and then a follow-up video with the answers and explanations to the quiz questions. In this video, we will learn what object-oriented programming is. One of the most important concepts in computer programming is object-oriented programming. You may also see object-oriented programming as the acronym OOP. Object-oriented programming is a type of software design in which programmers can make their own data structures with methods that can be used on them. What does all this mean? We've learned about the basic data types like Booleans, characters, integers, and floats. We've also learned about containers and data structures like vectors, lists, decks, sets, and maps. What if I wanted to write a computer program that dealt with cars? Currently, there is no way for me to tell the computer I want to have a car type that I can reference. Great news! Using object-oriented programming, you can create classes and objects that represent cars, zombies, animals, or anything else you like. OOP allows us to create a custom data structure that becomes an object, and includes both data, information that describes the object, and functions, allowing us to do things with the object. For example, a car may have an int variable for its speed, a float variable for how much gas it has in it, and a string variable for the make and model. The car object may have functions like drive and brake. We could call the drive function to move the car. The brake function could be used to stop the car from moving. Another key principle that object-oriented programming makes accessible to us is the ability for programmers to create relationships between objects. For example, one object can inherit characteristics from another object. If you're planning on working professionally as a software engineer or are preparing for an interview, object-oriented programming is one of the most important concepts to understand. Up until this point in the course, we have been writing functions and using them to solve problems. We have not been tapping into OOP to solve problems. When you just use functions to solve problems, that is called procedural programming. A function or procedure contains a series of computational steps to be carried out. There are several advantages to object-oriented programming over procedural programming. One big advantage of object-oriented programming is when we want to create a new object, we can inherit features from existing objects, making it easier and quicker to create the new object. Object-oriented programming languages are high-level languages that are based on the object-oriented model. In other words, they support classes and objects. In order to write object-oriented code, you need to use an object-oriented programming language. As you may have guessed or may already know, C++ is an object-oriented programming language. Other examples of object-oriented languages are C#, Python, and Java. There are four main object-oriented concepts. We call them the four pillars of object-oriented programming, as they are the basis for what OOP allows us to do. The four pillars of object-oriented programming are encapsulation, abstraction, inheritance, and polymorphism. In this video, we will learn about the four pillars of object-oriented programming. There are four main concepts or pillars in object-oriented programming. These are the core, fundamental concepts of OOP that empower developers to write object-oriented code. The four pillars of object-oriented programming are encapsulation, abstraction, inheritance, and polymorphism. Encapsulation means making a class's attributes inaccessible from other classes. We should write code in a way that each class is like its own unit. Variables or data inside of a class should be hidden from any other classes and can only be accessed inside of that class. We also call encapsulation data hiding or information hiding. Abstraction, put simply, is hiding the details of the program from the end user. If we built an app, the user could click a button to perform a task, but doesn't need to understand all of the code running under the hood to make the app work. Abstraction also means hiding the details from other parts of the program. One object does not need to know or understand what another object does, it just needs to know which objects are available to call, and which kinds of parameters are needed to trigger a certain operation. Inheritance is used to add the functionality of one class to another class without having to rewrite the logic. A derived class or subclass means that fields and methods from the parent class are inherited. Polymorphism means that classes can have different functionality while sharing a common interface. In other words, objects can take on multiple forms. A shape can be a rectangle, triangle, circle, etc. All of these things are shapes, but they are all different forms of a shape. In this video, we will learn about classes in C++. Classes are the building blocks of object-oriented programming. A class is the blueprint for an object. Classes can have variables and functions. We refer to the variables in a class as the class's attributes. Functions inside of a class are called methods. To create a class, we use the class keyword. For example, we can use the class keyword and create a class named example class. Notice the curly braces after the name of the class, inside of which will go the code for this class. Also notice that we had a semicolon after the closing curly brace. Inside of our class, we are going to use the public access modifier, which means that anything beneath it can be accessed by code outside of the class. Let's create an int attribute named integer field. After that, we will add another attribute to our class, a char variable named character field. Next, let's add a bool named boolean field to our class. We can also add a float named floating point field to our class. Now our example class contains four attributes, an int named integer field, a char named character field, a bool named boolean field, and a float named floating point field. Let's add some methods to our class. For example, we can create a void function named method1, and inside of there we will output the string method1 to the console. We will also create a method with a void return type named method2, and inside of here we will output the string method2 to the console. In this video, we will learn about working with objects in C++. We create an object from a class. Since we have our class named example class that we created in the last video, we can use this as a blueprint for creating objects using C++ code. The first step is to declare the object. To do this, we type the name of the class and then the name of the object. For example, let's create an object of type example class named obj. Since the attributes were marked as public in our class, we can set them here. We access the attributes and methods of an object using the dot operator. For example, let's assign the object's integer field a value of 15. Then we will set the character field to the character value a. Next, we will set the Boolean field equal to true. After that, we will set the floating point field equal to a value of 3.5f. We can also call the methods of our class on the object. For example, let's call method 1. Then we will call method 2. When we run the code, notice that these methods were run, and the console shows the output messages method 1 and method 2 respectively. In this video, we will learn about inheritance in C++. Before we jump into what the concept of inheritance means in code, let's understand it with an example first. Inheritance is when one object is a type of another object. For example, there are different types of vehicles. Each vehicle is able to move at a certain speed. A car and a plane are two examples of vehicles that move at different speeds. When a car moves, it is driving. When a plane moves, it is flying. Let's use the object-oriented programming concept of inheritance to turn this basic conceptual example into code. First, we will create a class named vehicle. Inside of here, we will use the public access modifier. Let's create a function with a void return type named setSpeed, which will take in one parameter, an int s. Inside of this function, we will set the speed of our vehicle equal to s. Next, we will use the protected access modifier. Let's have a variable of type int named speed and a function with a void return type named move. Inside of this function, we will output the message vehicle is moving to the console. Vehicle is going to be the base class for the car and plane classes that we create, meaning that both cars and planes will be vehicles. Let's create a class named car. To make a class inherit from another class, we put a colon, then the public keyword, and then the name of the base class, which is vehicle in this case. Inside of this class, we will create a public function with a void return type named move. Recall that our base vehicle class also has a function named move that has a void return type and doesn't take in any parameters. When a child class defines its own version of the base class's function, we call that overriding the function. So in this case, the car class overrides the vehicle class's move function. Inside of this function, we will output the message car is driving at a speed of, then the speed, and then a new line to the console. Next, we will create a class named plane, which extends the vehicle class. Inside of here, we will use the public access modifier and have a function with a void return type named move. Inside of this function, we will output the string plane is flying at a speed of, then the speed, and then a new line to the console. Next, we will go inside of C++'s main function. Let's create an object of type car named car. Then we will call the car's setSpeed function and pass in a value of 60. After that, we will call the car's move function. Next, we will create an object of type plane named plane. Let's set the speed of the plane to 100, and then call the move function. Let's ensure that we have a semicolon at the end of each class, like the plane class, which ends on line 29. When we run the code, notice that the messages car is driving at a speed of 60 and plane is flying at a speed of 100 were output to the console. I want to show you how you can call the base class's function. For example, let's go inside of the plane class's move function and remove the code that is currently present inside of there. Then we will type vehicle with a capital V, colon, and then make a call to the move function. This is telling the code to call the vehicle class's move function whenever the plane class's move function is called. When we run the code, notice that the phrase vehicle is moving was output to the console. In this video, we will recap the key takeaways from the material we learned in this section of the course. Object-oriented programming, or OOP, is code that works with classes and objects. C++ is an object-oriented programming language, along with languages such as Java, C#, and Python. There are 4 pillars in object-oriented programming: inheritance, encapsulation, abstraction, and polymorphism. Encapsulation means making a class's attributes inaccessible from other classes. Abstraction, put simply, is hiding the details of the program from the end user. Inheritance is used to add the functionality of one class to another class, without having to rewrite the logic. Polymorphism means that classes can have different functionality, while sharing a common interface. Classes are the blueprints of objects. A class can have variables, aka attributes, and methods, aka functions. We instantiate objects out of classes. Classes and objects are the fundamental building blocks in object-oriented programming. Inheritance means that one class can extend another class, along with its attributes and methods. In this video, we will go over the answers and explanations to the quiz questions. The first question is a true or false question that asks us whether or not C++ is an object-oriented programming language. The answer is true. C++ supports programming with classes and objects, and is therefore an object-oriented programming language. Question 2 asks which concept means making a class's attributes inaccessible from other classes. The answer is encapsulation. Question 3 says blank means many forms and that classes can have different functionality while sharing a common interface. The answer is polymorphism. Poly means many and morphism means forms. In this section, we will use our C++ programming skills to solve some common string algorithm questions that you may encounter if you go on a coding interview. We will learn how to solve string to integer, palindrome, reverse words in a character array, valid parentheses, and valid anagram problems. Then we will recap the key takeaways we learned in this section of the course. By the end of this section, you will have experience using your C++ programming skills to work with string algorithms, and be prepared for questions about string algorithms that could come up on a coding interview. In this video, we will learn about the Roman to integer question and plan out the algorithm to solve it. The question tells us that Roman numerals are represented by 7 different symbols: I, V, X, L, C, D, and M. Each of the letters has a number value it corresponds to here. Additionally, we are told that certain combinations of symbols have other number values. So the full list of symbols to ints is as follows. The problem asks us to write a program that converts a Roman numeral to an integer. To solve this problem, here's what I'm thinking. We will store each of the symbols and their corresponding integer values in a map. For each letter, we will check if it is a 2-letter combo or is a single letter, and assign it a numerical value based on that. Finally, we will add up the total value and return that at the bottom of our function. The end result will be a program that converts a Roman numeral string to its integer value. In this video, we will go over the answer and explanation to the coding exercise. At a high level, here are the steps I'm thinking of to solve the problem. Since the question has strings that correspond to different number values, this could be a really good spot to use a map, mapping the Roman numeral string to its corresponding integer value. We'll use a vector to store substrings that we find in the input string s. Each time we find a substring, we will push it onto the vector. After we've broken the string into its substring Roman numerals, we'll iterate over our list of substrings and add their values to the total, using the string to int map we made at the start. We'll return the total at the bottom of the function. Inside of the Roman to int function, let's create an int variable named total, initialized to a value of 0. Then we will declare a vector of strings named strings. After that, we will have a map with keys as strings and values as ints, named symbol to values. We are going to populate this map with the string values of the Roman numerals as keys and their corresponding integer values. Let's add the following key value pairs, mapping the string I to the int 1, v to 5, x to 10, l to 50, c to 100, d to 500, m to 1000, iv to 4, ix to 9, xl to 40, xc to 90, cd to 400, and cm to 900. Next, we are going to have a for loop that starts at int I equals 0, runs while I is less than s.length, and increments I by 1 each time. Inside of this for loop, we will check if the substring at index I is equal to the Roman numeral character I. If that is the case, then this Roman numeral could be one of 3 values within the larger number. It could be IV, a value of 4, IX, a value of 9, or I, a value of 1. So before we assume that it has a value of 1, we are going to need to check the next character in the string. First, let's check that I plus 1 is less than s.length, meaning that it does not exceed the length of the string. Then we will use the AND operator, and also check if s at index I plus 1 is equal to the Roman numeral character v. If so, we will add the string iv to our strings vector using the pushback function. Since we have accounted for 2 characters in the string, we need to increment I by 1. This will move the iterator for the for loop 1 spot to account for the I. And then the for loop does the I++, moving it past the v character, and then we are on the next character in the string. Else if I plus 1 is less than s.length, and s at index I plus 1 is equal to the character x, we will add the string ix to our strings vector, and then increment our iterator variable I using the ++ operator. Else we will add an I to our strings vector, because if it didn't have a v or an x in front of it, then we know that it is a single I that corresponds to a value of 1. In an else if statement, we will check if the character at index I in the string is x. If it is, we will check if I plus 1 is less than s.length, and s at index I plus 1 is equal to l. If so, we will add the string xl to our strings vector, and then increment I. Else if I plus 1 is less than s.length, and s at index I plus 1 is equal to c, we will add the string xc to our strings vector, and then increment I by a value of 1. Else we will add the string x to our strings vector. Else if s at index I is equal to c, we will check if that character after it is a d. If so, we will add the string cd to our strings vector, and then increment I by 1. Else if the character after the c is m, we will push the string cm onto our strings vector, and then increment I. Else we will add c to our strings vector. We will have an else statement to the outer if else if statement that we wrote. Inside of here we will create a string named char as string, and use the string constructor to convert s at index I to a string of length 1. Then we will add char as string onto our strings vector. Outside of the conditional logic, we will iterate over each string, which we will call Roman, in our strings vector. We will add the corresponding int value to the total using the map of the symbols to values we created earlier. At the bottom of the function, we will return total. On line 36, we need to make sure the character D has single quotes around it, not double quotes, so that we don't get an error when running the code. When we run the code to test our solution, notice that it is correct. In this video, we will take a look at the algorithm for checking if a string is a valid palindrome. A phrase is a palindrome if, after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters include letters and numbers. Given a string S, we are asked to return true if it is a palindrome or false otherwise. One approach we could take to solve this problem is to convert each character in the string to lowercase, remove all non-alphanumeric characters from the string, reverse the string, and check if the forwards and backwards strings are equal. If so, then we know that the string input into the program is in fact a palindrome. In this video, we will go over the answer and explanation to the is_palindrome coding exercise. Up at the top of the code, we will include the IO stream, string, regex, and locale header files. Inside of our is_palindrome function, we will create a string variable named s lowercase. Then we will create a variable of type locale named loc. Next, we will iterate over each element named elem in string s. Inside of this for loop, we will add the lowercase version of the letter to our s lowercase string by using the toLower function and passing in elem as the first argument and loc as the second argument. After that, we will create a variable of type regex named expr that we assign the regular expression caret lowercase a through lowercase z, uppercase a through uppercase z, and 0 through 9. Then we will set s lowercase equal to a call to regex replace and pass in s lowercase as the first argument, expr as the second argument, and an empty string as the third argument. Then we will create a string variable named reverse. After that, we will have a for loop that starts at int I equals s lowercase dot length minus 1, runs while I is greater than or equal to 0, and decrements I by 1 each time. Inside of this for loop, we will add s lowercase at index I to a reverse string. At the bottom of the is_palindrome function, we will return the result of a function call to s lowercase dot compare with reverse passed in, and whether or not that value equals 0. If the compare function returns a value of 0, we know that s lowercase and reverse are equal to each other. When we run the code to check our solution, notice that it is correct. In this video, we will go over the concept of the reverse words in a character array problem we will solve and understand the algorithm for it. The question asks us to write a function that reverses a string. The input is given as an array of characters s. It also informs us that we must do this by modifying the input array in place with a constant space solution. Constant memory or space means that we can't create a new array to populate with values. We need to modify the existing one. Also, note the words in place, which means editing the given array and not creating a new one. The algorithm I am thinking of using to solve this question is to have one variable starting with index 0 and another with an index of size of the array minus 1. We will swap the elements of these indices and then move the left pointer forward by 1 spot and the right pointer back by 1 spot. Eventually, by swapping the values, we will have reversed the entire array. In this video, we will go over the answer and explanation for the reverse string coding exercise. Inside of the reverse string function that we are provided, we are going to create an int variable named index1, initialized to a value of 0. We will also create an int variable named index2, set to a value of size minus 1. After that, we are going to create a char variable named temp that will be used during the swapping of the characters. Next, we will have a while loop that runs while index1 is less than index2. Inside of here, we will swap the character at index1 with the character at index2. To do this, the first step is to save the value of s at index1 to temp, so we will set temp equal to s at index1. Then we will set s at index1 equal to s at index2. After that, we need to set s at index2 equal to temp. Next, we will increment index1 and decrement index2. That wraps up our code to reverse a string in C++. When we run the code to check the solution, notice that it is correct. In this video, we will take a look at the valid parentheses question we will be solving, and gain an understanding of an algorithm we could use to solve it. The question asks us, given a string s containing just the characters opening parenthesis, closing parenthesis, opening curly brace, closing curly brace, opening square bracket, and closing square bracket, determine if the input string is valid. An input string is valid if open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order, and every closed bracket has a corresponding open bracket of the same type. My idea for solving this question is using the stack collection type from the standard template library. Iterating over the string, we would add each of the opening parentheses, curly braces, and square brackets to the stack. If we hit a closing delimiter, we will check if it matches the type of opening delimiter. If it does, we can continue. Else, we can return false because there is a mismatch. If we get to the end of the for loop and our stack is not empty, we will return false. If we hit a closing delimiter, we will pop off of the stack and check if the popped value matches the type of the opening delimiter. If it does, we can continue. Else, we can return false because there is a mismatch. If we get to the end of the for loop and our stack is not empty, we will return false as well since there is one or more characters left over on the stack after our algorithm has completed. In this video, we will go over the answer and explanation to the valid parentheses coding exercise. At the top of the code, we will include the string and stack header files, since our program will be making use of these two data structures. Inside of the isValid function, we will create a stack of characters named opening delimiters. Then we will have a for loop that starts at int I equals 0, runs while I is less than s.length, and increments I by 1 each time. Inside of this for loop, we will check if s at index I is equal to an opening parenthesis, or curly brace, or square bracket. If so, we will push s at index I onto our opening delimiter stack. Else, we know that the character we are on is either a closing parenthesis, curly brace, or square bracket. Inside of here, we will first check if the size of our opening delimiter's stack is equal to 0, meaning it is empty. If that is the case, we will return false. After that, we will have a char variable named start that we set equal to opening delimiters.top. Next, we will pop the top element from the opening delimiter's stack. Then we will create a Boolean variable named isInvalidCombo that we set equal to a Boolean expression checking if s at index I is a closing parenthesis and start does not equal an opening parenthesis. After that, we will have a bool variable named isInvalidCombo, which we set equal to a Boolean expression checking if s at index I is equal to a closing curly brace and start does not equal an opening curly brace. Then we will have a bool variable named isInvalidCombo that we set to a Boolean expression checking if s at index I is equal to a closing square bracket and start does not equal an opening square bracket. If is invalid parentheses combo or is invalid curly braces or is invalid square brackets combo are true, we will return false. At the bottom of the function, we will return the result of a Boolean expression checking if opening delimiters dot size is equal to 0. When we run the code to check our solution, notice that it is correct. In this video, we will go over the valid anagram question and algorithm. The problem tells us given two strings, s and t, return true if t is an anagram of s, and false otherwise. We are also given the definition of an anagram, which is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all of the original letters exactly once. In other words, both strings need to have the same count of the same letters. The algorithm I am thinking of is to first go over each letter in string s, and create a map of each letter and the count of times that the letter appears in the string. Next, we will go over each letter in string t and check if the map doesn't contain it, or if the count of that letter in the map is 0. If either of these conditions is ever met while our algorithm is running, then we can return false. Each time we hit a letter that is in the map, we will decrement the count associated with it. After that, we will go over each letter in the map. If it has a count other than 0, we know that we haven't used all of the letters, and therefore the strings are not anagrams. Else, if the count of all the letters in the map is 0, we know that the two strings are anagrams. In this video, we will go over the answer and explanation to the valid anagram coding exercise. Up at the top of the code, we will include the string and map header files, since our solution will make use of strings and maps. Inside of the isAnagram function, we'll first create a map that has strings as keys and integers as values, named letters and counts. For each character c in our string s, we will create a string named c as string, and pass 1 as the first argument in the constructor, and c as the second argument in the constructor. Next, we will have an if statement that checks if c as string is not an existing key in our map, which we can do by using the count function. If the key doesn't exist in our map, we will add it to the map and assign it a value of 1, since this is the first time we hit that letter in the string. Else, we can increment the value in our map since the letter exists as a key in the map. This for loop builds a map that contains each character in the string as a key, and the count of the times each letter appears as the value corresponding to that key. The next step is to iterate over each character c and t, the other string that is a parameter that gets passed into our function. Inside of the for loop, we will create a string variable named c as string, which will be the character c converted to a string. We will pass 1 in as the first argument to the constructor, and c as the second argument to the constructor. If we hit into a letter that does not exist in the dictionary, or whose count is 0, we will return false, since that means that we don't have one of the letters we need in string s to make the string t. Else, we will decrement the value of c as string in our letters and counts map. After that, we will create an iterator for our map of strings to ints, named it. We will iterate over each key in the map and check if the count of any of the letters is not equal to 0. If that is the case, we will return false, since we know that there is a letter left over, and therefore the two strings s and t are not anagrams. At the bottom of our function, we will return true, since if the code gets to this point, we know that the two strings are anagrams. When we run the code to check our solution, notice that it is correct. In this video, we will recap the key takeaways from the material we learned in this section of the course. In the Roman to integer question, we created a program that converted a Roman numeral string to an integer. When tackling this question using C++, maps can help us out tremendously. For the palindrome question, we crafted a C++ program that determined if a string is a palindrome. A palindrome is a string that reads the same forward and backward. Reversing the characters in a character array can be accomplished by using two pointers, one starting at the beginning of the array and one starting at the end of the array, and moving them closer to each other using a temp variable to swap the elements of those indices until the pointers meet in the middle of the array. The valid parentheses question gave us an opportunity to use the last in, first out, or LIFO property of the stack collection type. Anytime we hit an opening delimiter, we pushed it onto the stack. When we encountered a closing delimiter, we popped the top value from the stack and checked that it was the proper opening type of delimiter corresponding to the closing one. For the valid anagram question, we made use of the map collection type and stored the letters as keys and their counts in the string as values. Recall that an anagram is when a word uses the same letters in a different order. In this section, we will use C++ code to solve some array algorithm questions that are commonly asked on interviews. The array algorithms we will learn about are remove element, remove duplicates from sorted array, Pascal's triangle, and sort array by parity. After that, we will recap the key takeaways from this section of the course. By the end of this section, you will understand how to solve commonly asked array algorithms using C++ code. In this video, we will go over the remove element question and an algorithm we could use to solve it. The question is as follows. Given an integer array nums and an integer val, remove all occurrences of val in nums in place. The relative order of the elements may be changed. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array nums. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Return k after placing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place with constant extra memory. The values in the array are between 0 and 100 inclusive. Here's the algorithm I'm thinking of using to solve this question. We'll start out creating a count that gets initialized to the size of the given array. Since the numbers in the array are between the values 0 and 100, we can iterate over each int in the array, and if it equals the specified value passed into the remove element function, we can set it to 101. Then we will need to sort the array in place. After that, we will iterate over each number in the array, and if it is equal to 101, we will decrement the value of count. At the end of the function, we will return count. In this video, we will go over the answer and explanation to the remove element coding exercise. At the top of the program, we will include the vector, algorithm, and cassert header files. Inside of the remove element function, we will create an int variable named count, initialized to nums.size. After that, we will have a for loop that starts at int I equals 0, runs while I is less than nums.size, and increments I by 1 each time. Inside of this for loop, we will check if nums at index I is equal to val. If so, we will set nums at index I equal to 101. Next, we will sort the vector in place, which we can do calling the sort function, and passing in nums.begin as the first argument, and nums.end as the second argument. After that, we will have a for loop that starts at int I equals 0, runs while I is less than nums.size, and increments I by 1 each time. Inside of this for loop, we will check if nums at index I is equal to 101. If so, we will decrement count. At the bottom of the function, outside of the for loop, we will return count. In this video, we will go over the question for removing duplicates from a sorted array, and come up with a potential algorithm to solve the question. We are asked, given an integer array nums sorted in non-decreasing order, remove the duplicates in place such that each unique element appears only once. The relative order of the elements should be kept the same. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array nums. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Return k after placing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place with constant extra memory. In terms of a strategy to solve this problem, here's what I am thinking. We will have a variable last element that holds the first element in the array. It will be updated to store the last element we processed on the prior iteration. We will also have a variable initialized to the amount of items in the array. We will iterate over each element in the array, starting with the second one. If that element matches the value stored in last element, we know that it is a duplicate. We will set it to 101 and then decrement count. Else we will set last element equal to the element that we just processed. At the bottom of the function we will sort the array and then return count. In this video we will go over the answer and explanation to the remove duplicates from sorted array coding exercise. At the top of the code we will include the vector, algorithm, and cassert header files. Inside of the remove duplicates function we will create an int variable named last element that we initialize to nums at index 0. Then we will create an int variable named count that we set equal to the length of the nums vector, obtained by the size method. For int I equals 1 while I is less than nums.size, incrementing I by 1 each time, we will check if nums at index I is equal to last element. If so, we will set nums at index I equal to 101, and then decrement count. Else we will set last element equal to nums at index I. At the bottom of the function we will call the sort function and pass in nums.begin as the first argument, and nums.end as the second argument. Finally, we will return count. When we run the code to check our solution, notice that it is correct. In this video we will discuss the Pascal's triangle problem and plan out an algorithm to solve it. Given an integer num rows, return the first num rows of Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it, as shown here. To solve this problem, I am thinking we have two vectors. One will be the full result we return, and the other will be a sub-result that holds the numbers for the level we are currently processing. We'll start out by adding 1 to the sub-result vector. Then, for each of the middle cells in the triangle, we will calculate the sum of the two above it, and use that value for the result in the cell we are currently on. At the end of each row will be a cell with a value of 1. After we process a row, we will add subresult to the result vector. At the end, we will return the result vector, which will be holding the solution that our algorithm created. In this video, we will go over the answer and explanation to the Pascal's triangle coding question. At the top of the code, we will include the vector header file. Inside of our generate function, we will create an int variable named sum, initialized to a value of 0. Then we will create a vector storing vectors that store integers and name it result. This will be the full list that we return at the end. For int I equals 0, while I is less than num rows and incrementing I by 1 each time, we will create a vector of ints named subresult. Then we will have a for loop starting at int j equals 0, running while j is less than or equal to I, and incrementing j by 1 each time. Inside of this for loop, we will check if j equals 0. Inside of the if statement, we will add 1 to our subresult vector using the pushback function. Else, if j is greater than 0, and j is less than or equal to I minus 1, else we will set sum equal to result at index I minus 1 j plus result at index I minus 1 j minus 1. After that, we will add sum to the subresult vector. Else, we will add 1 to the subresult vector. Outside of the inner for loop, but still inside of the outer for loop, we will add the subresult vector to the result vector using the pushback function. At the bottom of the function, we will return result. When we run the code to check our solution, notice that it is correct. In this video, we will discuss the sort array by parity question and plan out an algorithm we will use to solve it. The question poses the following. Given an integer array nums, move all the even integers at the beginning of the array, followed by all the odd integers. Return any array that satisfies this condition. The solution I'm thinking of is to sort the elements in place and keep track of where the evens currently stop with a variable. We will iterate over the array, and if we hit an even number, we will increment this pointer to the end of the evens. Else, if the number is odd, we will keep going through the list until we find an even number, and swap the even and odd numbers. When this algorithm finishes executing, we will return an array that has all of the even numbers on the left and all of the odd numbers on the right. In this video, we will go over the answer and explanation to the sort array by parity coding exercise. Up at the top of the code, we will include the vector header file. Inside of the sort array by parity function, we will create a variable of type int named evens end pointer that we set equal to 0. Then we will have a for loop that starts at int I equals 0, runs while I is less than nums.size, and increments I by 1 each time. Inside of this for loop, we will check if nums at index I modulus 2 is equal to 0. In that case, we know we've hit an even number. Inside of this if statement, we will increment the evens end pointer. Else, we will utilize a for loop that starts at int j equals evens end pointer plus 1, runs while j is less than nums.size, and increments j by 1 each time. Inside of this for loop, we will check if nums at index j is even, by using the modulus operator with a value of 2 and checking if the result is 0. If so, we know we've hit an even number, in which case we can swap this number with the odd number currently at index I in the nums list. Inside of this if statement, we will create an int variable named temp that we set equal to nums at index j. Then we will set nums at index j equal to nums at index I. After that, we will set nums at index I equal to temp. Next, we will increment the evens end pointer and then break from the if statement. At the bottom of the function, we will return nums. When we run the code to check our solution, notice that it is correct. In this video, we will recap the key takeaways from this section of the course. The standard library's sort function takes in two parameters, a pointer to the starting position and a pointer to the ending position, which can be obtained using the begin and end functions respectively. The sort function will sort its elements in ascending order. In order to use the sort function, we need to include the algorithm header file at the top of the code. To obtain the number of elements in an array, we can use the size function. Indexing in C++ starts at 0. So the first element is at index 0, the second element is at index 1, etc. In Pascal's triangle, each number is the sum of the two numbers directly before it. Vectors are resizable lists and are useful when we want to be able to dynamically add elements to and remove elements from the list without having an exact fixed size of elements it can hold. To swap two elements in an array, we can store one value in a temp variable, set the first element equal to the second, and then set the second element equal to temp. In this section, we will learn about algorithms involving the tree data structure, and how to implement these algorithms using C++ code. The tree algorithms we will learn about are in-order traversal, pre-order traversal, post-order traversal, maximum depth of a binary tree, balanced binary tree, path sum, breadth first search, and depth first search. Then we will recap the key takeaways from this section. By the end of this section, you will understand many common tree algorithms that come up on coding interviews, and how to solve them using C++ code. In this video, we will learn about performing an in-order traversal on a tree. Our tree nodes are going to have string values, so the first step will be to include the string header file at the top of the code. Next, we will create a node class. Our node class will have three public attributes, a string named value, a node pointer named left, and a node pointer named right. An in-order traversal is when we visit the left node, then the root, and then the right node. So if we have an example tree with a root of B, a left child of A, and a right child of C, an in-order traversal would visit the nodes in the order A, B, and C. Let's look at how we would code an in-order function. We will create a function with a void return type named inOrder that takes in one parameter, a node pointer named root. Inside of this function, let's check if root equals null. If so, we will return from our in-order function. In-order is going to call itself, so it is a recursive function. This if statement is the base case that prevents the function from executing indefinitely. Under this if statement, we will make a recursive call to the in-order function and pass in root's left value. Then we will output root's value to the console. After that, we will make another recursive call to the in-order function and pass in the root's right value. That wraps up our in-order function. The next step is to go inside of C++'s main function and write the code we will use to test our in-order function. Let's create a node pointer named root that we set equal to a new node. After that, we will have a node pointer named left child set to a new node. Next, we will create a node pointer named right child, also set to a new node. Then we will assign root a value of B, left child a value of A, and right child a value of C. After that, we will set root's left value to left child, and root's right value to right child. Let's print out our tree to visualize it. First, we will output a few spaces, and then the root's value. Next, we will output a new line, then a forward slash, and then 2 backslashes, since 1 is used as an escape character. After that, we will output a new line, the left value of the root, then a few spaces, then the right value of the root. Then we will output 2 new lines to the console, and finally make a call to the inOrder function and pass in root. At the top of the code, let's make sure that we have a using statement importing the standard namespace. I'm also going to add an additional space in the string on line 34, so that the root of our example tree lines up properly in alignment with the other nodes. When we run the code, notice that our tree has B as the root, A as the left child, and C as the right child. Our inOrder traversal correctly traversed the nodes in the order A, B, and C. In this video, we will learn how to code a pre-order traversal on a tree using C++. Let's create a function with a void return type named pre-order that takes in 1 parameter, a node pointer named root. Inside of this function, we will check if root is null, and if so, we will return from the function. With a pre-order traversal, we go to the root, then the left node, and then the right node. So we will output the value of root to the console. Then we will make a recursive call to preorder and pass in root's left value. After that, we will make another recursive call to the preorder function and pass in root's right value. Finally, let's go inside of C++'s main function and call preorder, passing in root. When we run the code, notice that the nodes were traversed in the order B, A, C. In this video, we will learn about post-order tree traversal and how to implement post-order traversal using C++ code. Let's create a function with a void return type named post-order. It will take in 1 parameter, a node pointer named root. Inside of this function, we will check if root is null. If so, we will return from the function. A post-order traversal visits the left node, then the right node, and then the root. Let's make a recursive call to our post-order function and pass in the root's left value. Then we will make another recursive call to the post-order function and pass in root's right value. After that, we will output the value of root to the console. Inside of C++'s main function, we will make a call to the post-order function and pass in root. When we run the code, notice that the nodes are printed out in the order A, C, B, as expected. In this video, we will look at the maximum depth of binary tree question and plan an algorithm we can use to solve it. The problem poses the question, given the root of a binary tree, return its maximum depth. Furthermore, we are told that a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Usually tree questions involve a traversal or searching algorithm, and the two that usually come up are depth first and breadth first. A depth first traversal goes deep, visiting child and grandchild nodes before visiting a node's neighbors. In contrast, a breadth first search visits all of the neighbors before the children and grandchildren. To solve this question, a depth first algorithm would be the appropriate strategy to use, since the question is asking us to find the maximum depth. In this video, we will go over the answer and explanation to the maximum depth of binary tree coding exercise. At the top of the code, we will include the algorithm header file. Next, let's create a function with an int return type named depthFirstSearch, which will take in 2 parameters, a tree node pointer named root, and an integer named depth. Inside of this function, we will check if root is null. If that is the case, we will return depth. This will be the base case for our function. Else we will return the result of a call to max with a recursive call to depth first search, with root's left value passed in as the first argument, and depth plus 1 passed in as the second argument, and then another recursive call to depth first search with root's right value passed in as the first argument, and depth plus 1 passed in as the second argument. Inside of the max depth function, we will return the result of a call to the depth first search function, with root passed in as the first argument, and 0 passed in as the second argument. When we run the code to check our solution, notice that it is correct. In this video, we will look at the balanced binary tree question and plan out an algorithm to solve it. The problem statement tells us, given a binary tree, determine if it is height balanced. We are also given the definition of a height balanced binary tree. A binary tree in which the left and right subtrees of every node differ in height by no more than 1. We will need to determine the height of the subtrees, and then check that the absolute value of the right and left subtrees is less than 1. We will also need to make this check recursively on the right and left nodes' subtrees respectively. In this video, we will go over the answer and explanation to the balanced binary tree coding exercise. At the top of the code, we will include the algorithm and CMath header files. Next, we will create a function that returns an integer named getTreeHeight, which takes in one parameter, a pointer to a tree node named root. Inside of this function, we will check if root is null, and if so, we will return 0. Else, we will return a call to the max function, with getTreeHeight of root's left value passed in as the first argument, getTreeHeight of root's right value passed in as the second argument, and 1 added to the end. Inside of the isBalanced function, we will check if root is null. If so, we will return 1. Underneath this if statement, we will return a call to the absolute value function and pass in getTreeHeight of root's left value minus getTreeHeight of root's right value is less than or equal to 1, and a recursive call to isBalanced with root's left value passed in, and another recursive call to isBalanced with root's right value passed in. When we run the code to check our solution, notice that it is correct. In this video, we will look at the path sum problem and plan out an algorithm to solve it. The question says, given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. We can solve this question by using a depth first algorithm that executes recursively. In this video, we will go over the answer and explanation to the path sum coding exercise. First, we will check if root is null, and if so, we will return false. Then we will check if target sum minus the value of root is equal to 0, and root's left child is null, and root's right child is null, and if these conditions are true, we will return true. After that, we will return a recursive call to hasPathSum, and pass in root's left child as the first argument, and target sum minus root's value as the second argument. Next, we will use the OR operator and then make a recursive call to the hasPathSum function, and pass in root's right child as the first argument, and target sum minus root's value as the second argument. When we run the code to check our solution, notice that it is correct. In this video, we will learn about the breadth first search algorithm and how to implement it using C++. Let's look at an example using the tree shown here. The tree has a root node with a value of 1 that has a left child with a value of 2 and a right child with a value of 3. The tree has leaves with the values 4, 5, 6, and 7 respectively. With a breadth-first traversal or search, we visit a node's neighbors before visiting its children. So the traversal would start at the root node 1. Then we would visit 2 and then 3, since these two nodes are on the same level, aka neighbor nodes. After that, we visit the nodes 4, 5, 6, and 7. This completes the breadth-first traversal. Now that we understand the concept of a breadth-first algorithm, let's learn how to implement it using C++ code. At the top of the code, we will include the Q header file. After that, we will create a class named node with 3 public properties, an int named value, a node pointer named left, and a node pointer named right. Next, we will create a function with a void return type named breadth-first-search, which takes in one parameter, a node pointer named root. To implement a breadth-first-search, we can use a queue, since queues follow the principle of FIFO, first in, first out. As such, we will have a queue of node pointers named Q. Then we will push the root onto the queue. Next, we will have a while loop that runs while the queue is not empty. Inside of the while loop, we will have a node pointer named n that we set equal to q.front. After that, we will pop the front value from the queue. Next, we will log the value of n to the console. If n's left child is not null, we will push it onto the queue. In a similar fashion, if n's right child is not null, we will push it onto the queue. Next, let's go inside of C++'s main function. We will create some pointers to nodes for each node in our tree. Let's create a pointer to a node named root that we set to a new node. Similarly, we will have a variable named left child, a variable named right child, a variable named left child's left child, a variable named left child's right child, a variable named right child's left child, and a variable named right child's right child, each of which is a pointer to a node initialized to a new node object. After that, we will set root's value to 1, left child's value to 2, right child's value to 3, left child's value to 4, left child's value to 5, right child's left child's value to 6, and right child's value to 7. Then we will set root's left child to left child, and root's right child to right child. Next, we will set left child's left child to left child's left child, and left child's right child equal to left child's right child. After that, we will set right child's left child to right child's left child, and right child's right child to right child's right child. Next, let's output a visual representation of the tree to the console. Then we will make a call to our breadth-first-search function and pass in root. Up at line 11, let's ensure that we add a semicolon after the closing curly brace at the end of the class. I'll also make a couple spacing adjustments to the visual representation of the tree so that the values of the nodes print evenly spaced out. When we run the code, notice that a visual representation of the tree was output, and the breadth-first traversal output the values 1, 2, 3, 4, 5, 6, and 7, in that order, to the console. In this video, we will go over the answer and explanation to the breadth-first-search coding exercise. At the top of the code, we will include the Q header file. Inside of our breadth-first-search function, we will have a queue of node pointers named Q. Then we will push root onto the queue. While the queue is not empty, we will create a node pointer named n that we set to q.front. After that, we will pop the front element off of the queue. Next, we will output the value of node n to the console. Then we will check if n's left child is not null, and as long as it isn't null, we will push it to the queue. If n's right child isn't null, we'll push it onto the queue. When we run the code to check our solution, notice that it is correct. In this video, we will learn about the depth-first search algorithm and how to implement it using C++ code. With a depth-first traversal, the child nodes are visited before the neighbor nodes. For example, the traversal would start at the root 1. Then it would visit 3, 7, 6, 2, 5, and 4. When implementing a depth-first search algorithm, a stack is commonly used since stacks exhibit LIFO, last in, first out. Let's learn how to implement a depth-first algorithm using C++ code. First, we will need to include the stack header file at the top of the program. Next, we will create a function with a void return type named depth-first-search that takes in one parameter, a node pointer named root. Inside of this function, we will have a stack of node pointers named s. Then we will push root onto the stack. While s is not empty, we will create a node pointer named n that we set to s.top. After that, we will pop the top value off of stack s. Then we will output the value of n to the console. If root's left child is not null, we will push it onto the stack. If root's right child is not null, we will push it onto the stack. At the bottom of the main function, we will call our depth-first search function and pass in the root. When we run the code, notice that the nodes were traversed in the order 1, 3, 7, 6, 2, 5, and 4. In this video, we will go over the answer and explanation to the depth-first search coding exercise. At the top of the code, we will include the stack header file. Inside of the depth-first search function, we will have a stack of node pointers named s. Then we will push the root onto the stack. While the stack is not empty, let's create a node pointer named n that we set to s.top. Then we will pop the top element off of s. After that, we will output n's value to the console. If n's left child is not null, we will push it onto the stack. If n's right child is not null, we will push it onto the stack. When we run the code to check our solution, notice that it is correct. In this video, we will recap what we learned in this section of the course. There are 3 types of depth-first traversals on trees: in-order, pre-order, and post-order. An in-order traversal visits the left node, then the root, and then the right node. A pre-order traversal visits the root node, then the left node, and then the right node. A post-order traversal visits the left node, then the right node, and then the root node. A breadth-first search, or BFS, visits each of the neighbor nodes before visiting the child nodes. With this algorithm, a queue is used, since queues exhibit the FIFO property, first in, first out. A depth-first search, or DFS, visits each of the child nodes before visiting the neighbor nodes. With this algorithm, a stack is used, since stacks exhibit the LIFO property, last in, first out. In this section, we will learn about several linked list algorithms that come up on coding interviews. The algorithms we will learn about will be merging 2 sorted lists, removing linked list elements, and reversing a linked list. Then we will recap the key takeaways from this section of the course. By the end of this section, you will understand how to solve linked list algorithm questions using C++ code. In this video, we will look at the merge two sorted lists problem and plan out an algorithm to solve it. The question tells us that we are given the heads of two sorted linked lists, list 1 and list 2. We are asked to merge the two lists into one sorted list. The list should be made by splicing together the nodes of the first two lists, and we are to return the head of the merged linked list. To solve this question, I am thinking of having two pointers, one that goes through each list and checks which element is lower and then adds it to the list. Once one of the pointers is null, we will iterate over the rest of the elements in the other list and add them to our result list, of which we will return the head. In this video, we will review the answer and explanation to the merge two sorted linked lists coding exercise. The first thing we will do is create some pointers. Let's create a list node pointer named newHead, a list node pointer named pointer1 initialized to list1, a list node pointer named pointer2 initialized to list2, and a list node pointer named resultHead. If list1 equals null and list2 equals null, we will return null. Else, if list1 doesn't equal null and list2 equals null, we will return list1. Else, if list2 does not equal null and list1 equals null, we will return list2. If pointer1's value is less than or equal to pointer2's value, we will set newHead equal to pointer1. Then we will set pointer1 equal to pointer1's next value. Else we will set newHead equal to pointer2, and then pointer2 equal to pointer2's next value. After that, we will set resultHead equal to newHead. Next, we will have a while loop that runs while pointer1 does not equal null, and pointer2 does not equal null. Inside of here, we will check if pointer1's value is less than or equal to pointer2's value. Inside of this if statement, we will set newHead's next value equal to pointer1. Then we will set pointer1 equal to pointer1's next value. Else we will set newHead's next value to pointer2, and then set pointer2 to pointer2's next value. Outside of the if-else statement, but still inside of the while loop, we will set newHead equal to newHead's next value. While pointer1 isn't null, we will set newHead's next value equal to pointer1. Then we will set pointer1 to pointer1's next value. After that, we will set newHead to newHead's next value. While pointer2 isn't null, we will set newHead's next value to pointer2. Then we will set pointer2 to pointer2's next value. After that, we will set newHead equal to newHead's next value. At the bottom of the function, we will return resultHead. When we run the code to check our solution, notice that it is correct. In this video, we will look at the remove linked list elements problem and come up with an algorithm that we can use to solve it. The question reads, given the head of a linked list and an integer val, remove all the nodes of the linked list that have node.val equal to value, and return the new head. Basically, we are going to iterate over each element in the list, and if it has the val passed into the function, we will set the next value of the node before it to its next element, effectively removing it from the list. In this video, we will go over the answer and explanation to the remove linked list elements coding exercise. Inside of our remove elements function, we will have a list node pointer named resultHead, which will point to the head of the linked list that we will be returning from the function. Then we will have a list node pointer named priorNode, which will keep track of the last element we looked at. If head is null, we will return null. Next, we will set resultHead to head and priorNode to head. While head is not null, we will check if the value of resultHead is equal to the val we need to delete. and check if head's next value is not null. If so, we will set result head equal to head's next value. If head's value is equal to the val we need to delete, then we will set prior node's next value equal to head's next value. Else, we will set prior node equal to head. At the bottom of the while loop, outside of the conditional if-else logic, we will set head equal to head's next value, moving the pointer forward to the next node after each iteration of the while loop. Outside of the while loop, we will check if result head's value is equal to a val we need to delete, and if so, we will return null. At the bottom of the function, we will return result head. When we run the code to check our solution, notice that it is correct. In this video, we will look at the reverse linked list elements problem and plan out an algorithm to solve it. The question asks, given the head of a linked list and an integer val, remove all the nodes of the linked list that have node.val equal to val, and return the new head. We'll need to move through the list and set the next value of the node we are currently on to the previous node. Then, once we've reached the end of the linked list, we can return the previous node. In this video, we will go over the answer and explanation to the reverse linked list coding exercise. Inside of the reverse list function, we will have a list node pointer named current node that we set equal to head. Then we will have a list node pointer named previous node, initialized to a value of null, and a list node pointer named next node, also initialized to a value of null. If head is null or head's next value is null, we will return head. While current node is not equal to null, we will set node to current node's next value, current node's next value to previous node equal to current node, and current node equal to next node. At the bottom of the function outside of the while loop, we will return previous node. When we run the code to check our solution, notice that it is correct. In this video, we will recap the key takeaways from this section of the course. A linked list is made up of nodes. Each node contains a value and a pointer to the next node. Pointers play a key role in working with linked lists. We learned how to merge two sorted linked lists, remove linked list elements, and reverse a linked list using C++ code. Congratulations on finishing this course. First, we got introduced to C++ programming, beginning with setup on our machine, writing a hello world program, and the history of C++. Then we learned about the basics of C++. After that, we learned about obtaining user input, working with conditional statements, and loops. Next, we learned about user-defined types. Then we learned about intermediate C++ concepts like the standard library, working with dates and times, and recursion. After that, we learned about the various containers in C++. Next, we learned about object-oriented programming. Then we learned how we could use C++ to solve some of the main questions that come up on coding interviews, around the topics of string algorithms, array algorithms, tree algorithms, and linked list algorithms. Awesome job completing the course. By now you should have a great working knowledge of C++ code. I wish you the best of luck in your programming endeavors. If you are looking to learn coding, especially mobile app development, programming languages, information technology, game development, or web development, you've come to the right place. I currently have 21 published courses on Udemy, spanning these topics and more. I have several complete programming course, beginner to expert classes. Each of these courses aims at allowing you to master one programming language or platform. These are my complete C# programming course, beginner to expert, Ultimate Python, ML, AI, hacking speech recognition, and more, HTML and CSS Masterclass, Mastering IntelliJ IDEA and Android Studio, and Android Dev Masterclass Build 10 Apps, Java and Kotlin courses. If you're a beginner to coding and want to master the fundamentals in simpler languages like Python and JavaScript, I have a series of computer programming courses aimed at beginners. The sequence is as follows: computer programming for beginners, computer programming in Python and JavaScript intermediate, and advanced computer programming in Python and JavaScript. Are you getting ready for a coding interview, perhaps at a top-tier tech company? Prepare for any coding interview using my Coding Interview Masterclass in C# and JavaScript, where I teach you the approach to solving coding questions presented to you in an interview. Need help writing a resume and cover letter? My Fundamentals of Information Technology class has a full section on resume writing, cover letter preparation, and interview techniques. Demonstrate your ability to employers and maximize your skill set to land your dream job at a fantastic salary. Want to learn how to build video games? I have several courses on the topic of game development in Unity and build all kinds of exciting game projects hands-on like Pac-Man, a car racing game, Super Smash Bros., Super Mario, and more. If you want to take your Unity game programming skills to the next level, I highly recommend trying out my other most recent course, Master Unity and C# by developing 5 Super Mario games. Whatever your programming goals are, my courses will help you achieve them and carve out the career path of your dreams. If you have any questions about my courses, feel free to message me on Udemy or check out the free preview videos featured on the landing page for each course.